Alright, hell yeah. So we're going to revisit this problem. We got material mechanics, and it's a 2-star problem, and I guess I just solved it using a 1-star technique. You know what I mean? Any problem, it's good just to see if you can simplify it, and that's what we did. So the first thing that I'm going to show is just geometry. When it comes to material mechanics, kind of geometry is king. It's kind of what sets up the problem. And so we're going to have a center of mass of this bar when it's raised right there. And it's just, I think this is a bizarre property of mass. We do have a force of gravity, you know what I mean? So you have a force of gravity due to the Earth being, like obviously this experiment is operating on the surface of the Earth. So anything that has mass is going to have a force on it, like due to its weight. You know what I mean? We call weight a force. Usually you'll see something like that. Now weight is going to be mass times gravity. And if you're not sure of where that comes from, since we do have a 2-star problem, we're going to go over kind of some more. Everything is kind of going to be new for this, but just definitely more advanced concepts. So, you start with the force of gravity is gravitational constant, mass 1, mass 2, divided by the radius of the Earth squared. Mass 2 is the mass of the Earth, okay? And but at the end of the day, you also have Newton's equation that says, hey, one side of the equation is forces, and the other side is a mass that we've observed, and then acceleration. So with F equals ma, this equation says, hey, this side, the right side of the equation, is your observation. Hey, am I observing acceleration? Well, heck yeah. In this case, when I drop this, it was a velocity of 0. So anytime you want to identify acceleration, well, first, anytime you can identify something that has an initial velocity of 0, and then at some other point has a velocity of any velocity, you have a change in velocity. And that's all acceleration is. Acceleration is change in velocity, but also change in time. Change in velocity divided by change in time. Okay, but that's this side of the equation. This is what we observe. Now, this side of the equation is what we measure. Either with like a ruler or a scale, and this is not necessarily ruler and scale, but for like setting up experiments, because we set up multiple experiments. You can drop a mass. If you're anywhere near the surface of the Earth, down to up to the top of Everest, down to the sea level. That radius, and this radius is from the center of the Earth all the way to not only the surface of the Earth, but to where the center of mass, to this distance. Wherever you're doing the observation that day, the center of this bar to the middle of the Earth is this radius. Well, guess what? It's very difficult to even figure out what the radius of the Earth is exactly in your hometown. You know what I mean? Because how are you going to do that? So just know that it's going to be kind of an average. But anyway, and I guess we're going to slow this down, because that's what we do. Anytime that you can learn, something new, you might as well explore it all the way. And so the radius of the Earth, and you should be able to know everything that's going on with this equation just by using a couple simple guesses. And so what we're going to show is that the radius, just think, I don't know, science, just think the Christians are thinking science is of the devil, because you got a lot of sixes going on in this Kepler equation. You have the radius of the Earth is 6 times 6 to the 6. It's 6 times 10 to the 6, and that's in meters. So it's 6 million meters. That's the radius of the Earth. Cool. Now the mass of the Earth is 6 times 10 to the 24. So this one you just have to remember 24. I think that's an easy kind of round number to remember. and that's going to be in kilograms. Cool. And then the gravitational, and then so let's take a step back, because we've already said by experiment we know that we already know the force of gravity, but we do know it's related to this equation. So anytime you use Newton's equation of F equals ma, you have two sides. And this is where you're going to get confused. This is where I get confused doing physics problems. Is like, what side do things go on? Well, this side is the mass that we choose to observe. You know what I mean? Hey, look at that. We chose this bar as our mass, and we want to observe the acceleration. Now, this side is, hey, do we know what forces are acting on it? And by experimentation, we know that this bar is close to the Earth, and so we know that there's a force of gravity. Now, there might be other forces. Someone might be having their hand on this thing and winging it down. You know what I mean? So they use their arm to apply a force, and or you know what I mean? And then that force, you know, the second it leaves their hand, because anytime that it would be impossible just to touch it and then apply a force. The force is force over a distance, you know what I mean, or a force times time or whatever. So if you're winging it down with your arm, you're going to start here and then maybe let go here, and then that force is calculated, kind of the energy that you put in, because now this thing will have an initial velocity of like something, you know, of like 10 or whatever. But in our problem, the only force acting on this bar is gravity. So that's the only side of this equation. So then we can say, hey, we can throw in, you know, that's why in engineering you're just going to see this, mg. You know what I mean? And that's cool. You can go all 4 years. I got to throw some more time on the clock. Alright, heck yeah. So what I was saying is you can go like all 4 years of your college career just knowing that weight is mg, but then not realizing where that comes from. You know what I mean? So instead of starting a problem with just, oh, I know what weight is, it's mg. Well, and I know that gravity is 9.8. Well, why do you know that? You know what I mean? Because maybe you do want to take this problem to Mars, you know, build stuff on Mars, or the moon or something. That'd be pretty cool. Well, you got to start with Kepler's equation. So, and again, like, hey, this side is the mass that we're observing. This side is the experiments. We know that there's a field of gravity between one mass and a larger mass, no matter where you're at. But if we're on Earth, we're going to say that this side of the equation is g m1 me radius of the Earth squared. And then on this side you have m1, and that's the bar. This is m1. This is the mass that we're interested in, and its acceleration of 1. Well, now we can start kind of we can say that masses are on both sides of the equation, so we can just piece those out. And now we're just down to acceleration. Now we're gravitational constant, mass of the Earth, radius of the Earth squared is equal to the acceleration of that mass. So we can find the acceleration of the mass if we know the radius of the Earth squared, the mass of the Earth, and the gravitational constant. And this is pretty cool. This is where I'm going to throw an equal sign and then just put it over here. But 10, you know, every physics book says, you know, try to do problems in intervals of or magnitudes of 10, because then you're going to get to the answer more correctly. And so we can do that with this. I can say that I know that this is 6 times 10 to the 6 million meters, and I'm going to square it. Cool. And then I'm going to come up here and I'm going to say the mass of the Earth is 6 times 10 to the 24. Cool. And now what am I going to do? Hopefully I don't mess this up. Now, is the gravitational constant? That's what I was trying to figure out. Is like, what is the gravitational constant? Yeah, and it is 6. Like I kind of forgot it, but let's say I forgot it. All you need to do for this, there's 3 things going on here, and if you can remember 2 of them, you can get the other one, because we know this has to be 9.8, and 9.8 is approximately 10. So this all has to equal 10 to the 1. And going back to a lot of 6s going on here, we got a 6 there, a 6 there, a 6 there. Well, guess what? This is probably pretty close to 6. And this not only is close to 6, it's 6.66. Like that you could bet on that. And it's 6.66 times 10 to the what? Well, we don't know, and we don't need to get too crazy with this. We're just gonna say it's 6 times 10 to the something. It's negative 11. But this is one way to just memorize Kepler's equation by going by like, oh, there's 3 things here that I might not know, but I kind of know 2 of them. Like radius of the Earth and mass of the Earth, I always kind of have those in my pocketbook. This is kilograms, this is meters. And then obviously, acceleration is 9.8 or just 10. 10 to the 1. So I'm just going to say 10 to the 1. Cool. And then so if we have... So let's just do this real easy. We got 6 times 10 to the negative 11 times 6 times 10 to the 24 divided by and this you know I would square this all the way through or just do this 6 times 10 to the 6 and then 6 times 10 to the 6. Well, guess what? That 6 cancels that 6, that 6 cancels that 6, and now you have 10 to the 12 downstairs. Cool. And what do we know about 10 to the negative 11? Well, you can just bring that downstairs and it's going to be 10 to the 11. Now this is going to be 10 to the 12. And now upstairs you're going to have 10 to the 24. I think it's magic because now you have 10 to the 24 divided by 10 to the 23. 10 to the 24 minus... or 10 to the 24 divided by 10 to the 23 is just 10 to the 24 minus 23. It's 10 to the 1. You know what I mean? And I guess we'll do that. 10 to the 23 on the bottom. Well, this is just 10 to the 24. It's also 10 to the 24 times 10 to the negative 23. However you want to do it. But at the end of the day, it's 10 parentheses 24 minus 23 in the exponent. That's 10 to the 1. And you get 10. So, hell yeah. So now you have kind of this rough estimate that the gravitational constant is 6 times 10 to the negative 11. And just know that it's actually closer to 6.66. So, because it's closer to 6.66, that's a larger number, and that means that the... I don't know, probably this is just a little bit more than 6 million meters. You know what I mean? And then this is actually just a little bit less, 5.94. You know what I mean? Times 10 to the 24. I don't know if this 4 is accurate, but that 9 is hella accurate. So even just that, if you memorize 2 things, you know, and memorize a concept, and use this idea in physics of like, hey, I just want to know things by a factor of 10, so I'm not way off. Then numbers kind of have meaning. Then you can see this and this is like 6.67 times 10 to the negative 11. You know what I mean? Then you can kind of actually memorize numbers just a little bit better. But at the end of the day, yeah, it's cool to memorize numbers like pi is 3.1415. You know what I mean? Is it 29? Like, who cares, right? But 29? No, it's 3.14159. Yeah, because it should be 3.1416. But anyway, maybe I don't know that at all. Maybe I messed up. But you know, this whole foundation was just, you know, you should also have very vague ways of knowing things. You know, just and then powers of 10. Hey, I know that acceleration is 10. I know that the radius of the Earth is 6 times 10 to the 6. Mass of the Earth is 6 times 10 to the 24, and so forth. And you can get and this just works out perfect. You know what I mean? Okay, so we're going to use that concept and throw it back into our force equation. Well, yeah, and if you do this 100%, you get the acceleration is equal to 9.81. So now let's not lose what the heck we were even doing. So we were taking this mass. we wanted to observe the acceleration on this mass, and we observe that by experiment we know that there's a relationship between this mass and the mass of the Earth by the distance between those two objects, the centers of those two objects squared. Okay, and we can calculate that, so we can get the acceleration of that object is just gravitational constant, mass of the Earth, radius of the Earth squared. That's 9.81. What that means is that now we can what does that mean? Because I think actually it is kind of confusing to go back, because you still have two sides of this equation. So we're saying that and that was like this, like what we just did probably makes the most sense for just like an object that's just in free fall. Like you step off a cliff because you want to go cliff jumping. That's you. You know what I mean? You want to know maybe what forces are acting on you. Well, you got the force of gravity. And you actually, well, you might just want to know your acceleration. You know what I mean? That's something that we might want to know. Now, let's say you're just standing on top of the cliff still. You know what I mean? Hey, we're observing that your acceleration is 0. But now what gives? So let's do that one, because you're standing on top of that cliff. So what we do is we do a free body diagram. We actually just cut that. A free body diagram, how I explain it, is like literally do a dotted line around the object you want to do a free body diagram with, and then just pretend that object. More time on the clock. Alright, heck yeah. So draw a dotted line around the object you want to do a free body diagram on, and then just put it on your page, and then just pretend that it's totally in outer space. Like you know nothing about it, it's just in outer space. But you do know from observation like what's happening to that object. So if we're standing on a cliff, we know that there's no motion. Our velocity is 0, and then we wait some other time, and then we see that our velocity is still 0. So this is classic for material mechanics. We want to build bridges that aren't moving. You know what I mean? And so when we draw our dotted line around any object of our bridge, or in this case our cliff jumper, we say, hey, we know that when we do our F equals ma equation, so this equation says that, and you might not have any forces. Like let's say you're just in deep space, you know what I mean? This side of the equation could be 0 at that point. Well, we have 0 forces that we measured or statistically know about from experiments. And guess what? This mass will have 0 acceleration. You know what I mean? This equation kind of has to be balanced. But that's not the case, because the cliff jumper, well, guess what? We know that this cliff jumper is on the surface of the Earth, and it's got a huge Earth underneath them, and that Earth has a mass. So this side of the equation has to have. Now, and I think this is such a good place, because this brings up the normal force. That's kind of where we're going, and for the life of me, this just a weight with mg, I can get there. I can be like, cool, every weight is just mg, and I can just memorize that and just forget everything about Kepler's equation. But this next part, I just don't think you can just hand wave away, because it makes all of material mechanics, like the most important thing is like normal forces. So if you have like a bar that you cut at a 45, well, guess what? Now you have a perpendicular surface that is called kind of the normal force. You know, it's a surface normal perpendicular to the cut. And let's not go into that, but it applies to here, because we have and in this case, well, anyway, this will make more sense. So we do have a force. You are made out of particles that have mass, and you're next to a huge Earth. So you do have a force, even though you're not moving. There is, this side of the equation is not zero. This side of the equation, and if you want to do it correct, is gm1me radius squared. And let's just do the simplest. Let's say this isn't you, it's just a block that weighs 1 kilogram. So you have a 1 kilogram block at the top of the cliff. Well, cool. This is 1, and guess what you get? You get this side of the equation is, and then we'll say ma. So this brings up the topic of Newton's equation, 100% written, or you know, a couple ways to write it, is the sum of the forces. And this is all the vector forces. You know, any force in any direction, 360 degrees in the XYZ coordinate system. You can think of a spherical coordinate system. We all know 3D coordinate systems. It says that mass will have an acceleration. If there is a force, it'll have an acceleration also within that coordinate in some direction. The only way you can have a force on this side, because we have a force that's gm1me divided by radius squared, and then we're saying over here we observe zero acceleration. Well, if we do have that, m1 times 0, this equation is not balanced. And we really can't add anything to this side. This is just saying, hey, we have the mass and we want to observe motion or not motion. So we have to add something to this side of the equation. There must be another force on this 1 kilogram block sitting on top of that cliff. And that force is the normal force. And in this case, I think the thing that'll make the most sense is that if you have this force of gravity that's trying to pull it closer to the surface of the Earth, but we observe no acceleration, and this equation has to be balanced, well, we just have to minus the same thing we just wrote. So minus gm1me over radius squared. And what we just wrote here is the normal force. So this right here is the weight. Obviously this is the weight, because we said, and then to make this over here to actually make sense, because it's still kind of confusing, we're going to do this, m1, and then we're going to go gme over radius squared. And then didn't we just do this whole thing over here that we said, hey, this is gravity, this is that 9.8 number, you know what I mean? You throw in the correct gme and radius of the Earth squared, you'll get 9.81. And so now we have that 1 kilogram block, and this is where units matter, because if we do have this side, we have kilograms, and then gravity is in meters per second squared. And so how our units work is if we have 1 kilogram and we multiply that by 1 meter per second squared, this definitionally is 1 Newton. And if you think of F equals ma, that's saying over here, this left side is 1 Newton is equal to 1 kilogram. And I do these brackets to designate units, and I can also put a dot here to designate that I'm just showing kind of the units of an equation. And we got meters, 1 meter per second squared. All right, so heck yeah. So this weight, you know what I mean? Obviously, the weight of this, we're going to throw a W here. Well, that weight is just mg, and we said mass was 1 kilogram, and we got 1 times 9.8 meters per second. So in this case, in our case, we have 1 kilogram times 9.81 meters per second squared. I just meant to do parentheses. Okay, so if we said 1 kilogram times 1 meter per second squared, well, we got 9.8 of them, so this weight is 9.81 newtons. And that even might have been a little bit rushed on that. just showing that a 1 kilogram block, how much does that weigh? Well, it weighs 9.8 newtons. We all know, I think, just from basics, that 1 kilogram kind of weighs 2.2 pounds. And we know that, well, I would teach that 1 newton is a quarter pound. You know, that gets you kind of close. So if we have 9.8 of these, you can divide by 4, 9.81 divided by 4, and you're going to get 2.45 pounds. So it actually isn't a quarter pound, because another number to know is 9.44. So if you are going to divide newtons, don't divide it by 4, divide it by 4.44. And I think you can remember that. So 9.81 divided by 4.44, and you get that classic 2.20. And it's 2.2054, but for this basic one at 4.44, we get 2.209. You know what I mean? Could we do 4.444 to get more accurate? Well, at that point, I don't know, but you know. Anyway, so there you go. This 1 kilogram block, its weight, you know what I mean, just with the mg, is a downward force of gravity that's mass 1 kilogram times 9.81. So you got 9.81 newtons of weight on that thing. But guess what? So go back to here. Sum of the forces is equal to mass times acceleration. We're going to say we have a 9.8 Newton force, and that's going to be downward. So we can just do a negative sign if you want to do that. And we have to add something. That's going to be the normal force. It's just whatever force that's required to balance this equation. You know what I mean? And so there you go. And that's equal to mass times acceleration. We do not observe the block at the top of the cliff, you know, the person that hasn't jumped off yet. We don't observe them to be accelerating. So that part of the equation is 0, and you just bring, so we got negative 9.8 newtons plus n is equal to 0. Bring that over there. We got normal force is 9.8 newtons, the same as the weight. Alright, that concludes that little section. Now, this is different because we have a weight up here, center of mass, and then we have a pin right here. So we need to kind of simplify things again and say, hey, let's go back to our block on top of the cliff, and now the block decided to jump off. You know what I mean? So now we just do our F equals ma, and know that these are vectors or whatever. I guess it doesn't really matter. But the other part of this is it's written like sum of the forces is equal to mass times acceleration, and it could be sum of the accelerations. I think because these are vector quantities. But I can't take you down that path. But anyway, so right here, and we're just going to say, and we know that it's just going to fall in one direction. So we're going to say the forces in the y direction are equal times mass times the acceleration in the y. That's what we're going to observe. We're not going to observe any acceleration in the x direction. Okay, so we have, and we know that this weight is 1 times 9.8. 1. It's 1 kilogram times it's mg. That's the weight of that. Cool. So now we have on this side of the equation we have mg is equal to but that's it. We have no other forces. There is nothing. We are observing motion. So, you know, check it out. The second this thing steps off the cliff, we do observe motion. Its velocity was 0, and now at some point over here, its velocity is something. You know what I mean? And so that's significant because that means we have a change in velocity. Any observational change in velocity means that we have an acceleration. That's definitionally what acceleration is. Change in velocity, change in time. Okay, and we're going to neglect drag. You know what I mean? Obviously there's other air molecules here. You can be like, well, some of them are putting a force up. Yeah, and then so that would be mg. You know what I mean? Let's say that's downward. So we do negative mg plus force of friction upward, which would be well, and this is where physics problems get good. You know what I mean? Because sometimes drag coefficients are just, hey, some sort of number, some sort of constant that just makes everything just happy due to observation, and but it's a function of its velocity. You know what I mean? And so that's where it's just like, okay, now things get a little tricky, and that's going to be equal to the object's mass times its acceleration. So velocity in the y direction, acceleration in the y direction, and there you go. So these are the forces in the y direction. F of y is equal to may. But we don't have, let's just say we don't have air resistance, and then so we just have negative mg is equal to, and because we're saying that this is the positive direction. Sometimes they don't do that. They're like, well, if things are falling to the earth, we're going to call this the datum of 0. And then we're going to say this is positive distance, positive x. But in this case, we're going to say this is positive x, and this is in the negative. Positive y direction, and then a negative y direction. So we have negative mg and no other forces. So that's just equal to may. And the F equals ma. Is this part is the mass that you're trying to do the observation and analysis on. So, well, it just happens to be with Kepler's law that the force of gravity is this gravitational constant g if you're near the surface of the earth or anywhere between Everest and like the ocean floor, basically all the same, and that's g. I mean, it might be 9.7 top of Everest, could be, and then 9.9. But other than that, it doesn't get too much crazier than that. If you just guess 10, you're doing a pretty good job. All right, so these masses are basically the same. So now we can observe that negative g is equal to the acceleration that will the visible acceleration of the mass, and that's what we want. Acceleration of the y is negative g, and this is what we would observe on that block. Cool. Now we have to take it to something that's kind of more complicated, because we have a weight down here, but now this thing, so due to geometry, this is just a geometry problem where this mass can't be in free fall. It can't, because it's connected to this pivot. So if we follow the path of this mass, because here's the center, it's going to take a radially, it's going to take a quarter circle. It's going to take a circular path to get down here. And so this brings up, well, let's take a step back, because energy, okay, so if we know the acceleration of this block, we can be like, cool, we can know maybe how fast it's going to be when it hits the bottom of, like, let's say you're going off a 10-meter cliff. So you jump off what was that, like almost 40 feet? So you jump off a 10-meter cliff, and we want to know what's your velocity at the bottom. What's your final velocity? Well, you can use this F equals ma, because we found acceleration. And the acceleration right here is no different than when the block gets right here. It still is made up of particles of mass, and it still has this huge Earth underneath it. Kepler's equation says still that the force is mg. You know what I mean? You didn't get close enough to the radius of the Earth to increase that force, and and obviously you're getting closer. So this force is slightly increasing, but so negligible that that's why this is just a constant. It's just mg, but it's mg here as it was up there. So doing that same calculation, the acceleration right here is still negative g. That's the acceleration in the y. All right, so let's do that. Let's do this problem, because that's a foundational problem that is needed, to do this. Instead of just hand waving, I mean, at the end of the day, where we're going is we're trying to get to potential energy. We're trying to say that This has a potential energy of mgh, and we're going to say that this height is h. And by the time this mass gets to here, it's going to lose all its potential energy, and it's going to gain that in kinetic energy. It's going to have pure kinetic energy. Because energy can't be created nor destroyed, it can only just be transferred. You know what I mean? And there's no transfer of heat to this pin. There's no transfer to air, of heat and then air molecules actually moving. Because when air molecules have to accelerate out of the way, that's basically what drag is. You're taking air molecules that had a velocity of 0 and then pushing them out of the way. Well, to do that, to get an air molecule from here to there, you had to change its velocity. And if you had to change its velocity, it had to have an acceleration to do that. Every molecule of air has a mass, so now you have a mass acceleration, and a force had to do that. Remember Newton's law? A force has to be present. Force of friction for that air must be the mass of the air molecule times the acceleration that is required to push it out of the way. So that's cool. I mean, you probably just learned something right there. That's definitionally what air resistance is. Okay, so here we don't have air resistance, and so we don't, if we say, hey, we have an energy right here that's potential, and we're going to say, hey, that's going to equal this energy, well, that's true, but if you had like a fan trying to blow this, if it was like a board, and as it's falling, a fan is trying to blow it up, well, it's going to fall slower, you know what I mean? So it's going to take some of that energy, and some of that energy is going to be lost due to those molecules of air. Same thing, velocity of air is going to hit, and then those molecules are going to have to, so you have an initial velocity with a fan of air molecules hitting this board, let's say, and those molecules might come to a dead stop, on the face of that. So then that's going to be your change in velocity. An observed change in velocity means that you now have observed acceleration. Newton says, hey, a force is mass times acceleration. All right, heck yeah. So but we definitely need to know where we're going with this, because the basics of this problem are, heck yeah, you have a potential energy that's mgh. You can say when it lands, before it impacts this string, this is a nylon cord for the problem, and before it does that, it's going to have this mass and bar is going to have a velocity. So we could say that the mgh, the potential energy, is going to equal to the kinetic energy, because we're going to set this as the datum. That's how you can do that. You can say, hey, this is the datum 0, and you're going to say this height is that height. You know what I mean? So you're going to say mgh is equal to kinetic energy, which is 1/2 mv squared. Now, I'm not going to derive this one for this video, but we will probably kind of derive this scenario. Okay, so now that you know that it has kinetic energy and a velocity, well, guess what? From that point to stretching this string, which will just be a negligible distance. Materials don't stretch that far. So it's going to stretch this string, and then this mass is going to come to a dead stop. So the velocity will be 0. So we have velocity max is this, and that'll be velocity max. But within a very short distance, it's going to go to 0. And so we're going to say, hey, this kinetic energy is going to be, and when it does that, it's going to stretch this string. If this string stretches, it acts like a spring, and now you have energy stored in the string. So that's where the energy went. Purely, it went from potential to kinetic or velocity, velocity of a mass, and then that velocity of a mass went to 0, so 0 kinetic energy, and all that energy went into tensioning the string. And so the equation for the energy of a spring is 1/2 spring constant times the distance that the spring elongated squared. So it's 1/2 kd squared. All right, so this is basically, you know what I mean? So I could look at this problem and but I didn't know quite off the bat. Even when I looked at this, I was just like, oh, I still have to remember that even though I have a bar here that's connected to a pin, and when it swings, it's not like, and this is good because I can look at this problem now and be like, oh, like there's no place where friction is robbing this mass of any sort of energy, and then just any mass at height. You know, and I guess the take-home point on this one is just it seems magical. The fact that you do have a pin and then a center of mass of the bar, but it doesn't matter what this path is, you know, that the bar has to swing through. It only matters the vertical distance. And this comes up a lot in energy problems. Our force is only in the y direction. The force is in the y direction because the Earth is underneath us, and the center of the Earth to the center of this mass is more or less aligned. When this, but you know what I mean. If you want to know things 100%, well, heck yeah. When this bar comes over here, sure, there'll be a slight angle between this line and the center of the Earth. You know what I mean. That would be, if you wanted to do everything 1,000%. You know what I mean? That's the way you would do it, but that would be ridiculous. You know what I mean? This is a 2-star problem, not trying to figure out, oh, if you actually incorporated this angle in, you know what I mean, how would that change? Well, it would change your problem 0. You know what I mean? That change in that delta, that change or that angle between, you know what I mean? Okay, obviously. But this brings up the point that if you do the problem like this is where I did the problem wrong. Answer in the back of the book. Let's say we just wanted to find like the PSI, the pressure, the stress, the strength of this string. You know, might have a max pressure of like 60 megapascals, but we actually got it up to this equation says it's 33.1 megapascals, but the answer in the back of the book was 33.3 megapascals. And so that's what I'm going to be spending the remainder of the time exploring, is why the difference. And let's just talk about that. It's because I set this as my datum, but once this bar goes to horizontal, it starts to stretch this string. And then when it does, it might stretch the string that much. And now here is the new location of the bar. And so check it out. So this, the center of mass of the bar, actually moved down to here. Well, we have to incorporate that as potential energy. So now we have to kind of set this as our datum. You know what I mean? So now the datum is this distance plus h. And this is probably why this is a 2-star problem, because sometimes you'll just have like a thick metal collar, and then you know what I mean, that slams down on an impact hammer, and when it does that, it elongates the hammer. You know what I mean? So now the hammer is over here, and here's your change in length. So now mgh of this, you know, if we found the potential energy of this like steel collar, it has to be mgh, or it has to be mgh plus change in length, because here would be the datum of 0. Well, in this case, we're only going to say this is change in length. But what is this? Because this is at the halfway point, so due to geometry, this is going to be change in length divided by 2. So that's how you would represent that distance. You'd be like, well, I know this is change in length, and then this is going to be just half of that, because it's, you know, that it's halfway in between. It's just a little triangle there. I think you can see that. Okay, so for the actual problem, we say that the potential energy is mgh plus change in length. And now we're just going to we don't have to figure out what the velocity is. We can just say, hey, potential energy is equal to the energy stored in the spring. So I don't know how you'd write that, but just, you know, stored energy of spring energy. And so we're going to say that's 1/2 k, and then the d squared is change in length. And so we're going to say change in length squared. And then so we can this we can FOIL through. So essentially the potential energy is mgh plus mg change in length. And that's going to equal 1/2 the spring constant change in length squared. So right here, we want to solve for the change in length, because change in length is equal to our change in length max. That's our max change in length. And how these problems work, so we're gonna take the last 2 minutes before maybe going back to this, maybe not, because that might be for a full nother video of, like, you know what I mean, totally explaining. No, we'll probably go back to that. But so this is a quadratic. You know what I mean? If we rearrange this, we're going to say 1/2 k change in length squared, and then bring this over minus mg change in length minus mgh is equal to 0. And now we have this, this, and these are constants. So now we have something that says like ax squared plus bx plus c is equal to 0, where our a is 1/2 k, our b is negative mg, and our c is negative mg. No, mgh, I'm sorry. Whew, glad I caught that. So there you go. So now we would throw this into the quadratic equation and find our change in length. And it could be as simple as that, as just like, hey, just throw it into your calculator, because that's what I did right here, and I graphed it, and I found the 0 value, left bound, right bound, and then center. And then that stores as x into your calculator. So now we have change in length. I'm going to throw 10 more minutes on the clock, and we'll figure out how to do the problem exactly. And then I might explain this and show why this makes sense. Why the potential energy is just mgh. All right, hell yeah. So for this problem, yeah, you do have this quadratic, you find the change in length. And we did, and this change in length max, and that's 0.003965, whatever. It's in our calculator as the letter x. So now the problem says, well, what's this? And it says max stress, and stress is this sigma symbol. I use stress for like breaking. Like what's the like steel? Steel can take 58,000 psi, you know what I mean, pounds per inch squared. That means if you have 1 square inch of it, you can like hang 58,000 pounds, you know, kind of a semi. It's kind of the example that I use. But you can obviously take 1 square inch of steel and just hang, 58 pounds from it. You know what I mean? So then what would be the psi? Well, it would be, I don't know if that was a good example, but it would be 58 pounds per, well, that was a good example. 58 pounds per square inch should be 58 psi. So 58 pounds on a 1-inch steel rod, you'd have 58 psi in it. I think visually you can understand that. All right, so they want to know what's the max psi in the nylon cord. So we do our equation that stress or strength is force divided by area. But now we only know the change in length. So this goes back to the fundamentals of material mechanics. Is the first equation is strength or stress is force divided by area, and this is obviously you can weight a metal rod until it breaks, and then just record that number. Cool. That's the max force you can put on a 1-inch rod, and then that's how you get kind of strength, force per area. The other way is be like, oh, that rod, if it was steel and it was 1 meter, lengthened 0.002. So we have change in length, or strain, is change in length, or stretch, I call it stretch, it's strain, divided by L. And so for steel, that value of E max is going to be 0.002. But like I said, if you put 58 pounds on a 1 meter length of steel, well, it's going to be like 0.00, maybe 002. It might be, well, 1, 2, 3. Or it'd probably be 3 extra 0. It'd be a factor of 1,000 less than 0.002. Because we're putting a factor of 1,000 less max weight on it. You know what I mean? So anyway, and then our other equation that relates, I call this like a scale, and then this a tape measure, because we can actually measure the change in length, or we can like weigh something on a scale and find the max force. So what relates these two are strength is equal to EE, and this E is a constant. This is elasticity, and this is that stretch equation. This is strain. So this is strain, and I call it stretch, and this is strength, or also called officially stress. But yeah, just stress and strain is too confusing of terms. You'll have to use them, if you're writing textbooks or giving answers to your professor. But I just think it's really more basic. And at the end of the day, humans, we work in force. You know what I mean? Like, hey, how strong is something? If I buy a bolt at the store, how many pounds can I put on it? That's what I want to know. So at the end of the day, well, if I know the stress, I can find the force, and that'll be the number that makes more sense to me. Same thing here. If I know the strain, you know what I mean? Well, I can calculate the change in length, and that's observable. Like, I can observe that change in length, and that's important. So for this problem, you have these three equations, and you put them all together. So let's rewrite them. So you have stress is force over area. So any material mechanics problem, this is what you want to do. You want to write this one, and then stretch is change in length over L. And then you want to write strength is equal to EE. And then I would write a third, especially, and I would do this one. I would write this force of a spring. Force of a spring is K change in length. Because, hell, look at that. This change in length is synonymous with that change in length. Now we need to figure out what K is, but that comes out in the wash. So now let's put that aside. And when we rearrange these, this goes into there. So we'll have F divided by A on this side, and then this goes into here. We'll have change in length divided by length multiplied by the modulus of elasticity. So let's do that. Force over area is equal to change in length over length times modulus of elasticity. Okay. Now let's get this into a usable form. There's two usable forms. The most common one is finding change in length. So we'll go change in length is equal to L goes upstairs, E goes downstairs. So we're going to FL over EA. Spells flee if you go that way. That might be very helpful. But just being able to spit out this change in length is FL over EA. It's kind of that gold standard, that hard stop. Be like, I totally know that equation. And from this, I can rearrange and find the force. Because maybe I want to find the max force. Well, the force is going to be change in length, EA goes upstairs, divided by L. Cool. And now, to get this equation to look like this equation, that's where we kind of rearrange this. We're going to go, because the change in length is on the other side, so we're going to go F is equal to EA divided by L, and then put change in length kind of to the side. Well, this is totally equivalent. These two are equivalent, and we can see that the spring constant is EA over L. So we got our next equation. Anytime where we come across a spring constant, you know what I mean, for our spring or for our energy, we're just going to say K is equal to EA over L. Hell yeah, now we're on a roll, and that basically sums it up. Now, the other part of material mechanics that I do right off the bat, remember how I said this is strength? And it makes so much more sense if you call it strength. Because, you know what I mean, strength means like, hey, max stress. So just write the word max, and what's the other side of the equation? Well, it's got to be force max divided by area. This is strain, and again, that could have a max. So for steel, this is 58,000 psi, and for steel, this is 0.002, and it's unitless because it's change in length divided by length. But this is strain max is equal to change in length max divided by L. And so this is fundamentally what material mechanics is. It's like, hey, you just chose, I chose a 1-inch bar that was 1 meter long. And it could be anything. But I chose a 1 meter bar that has an area of 1 square inch. So I already chose my area. I already chose my length. And then from the material properties, these come out of the wash because they're material properties of steel. This is the max strength of steel. And this E is an equation that relates them. And you just do experiments. You take this specimen, and then you put 10 pounds, then 100, 1,000, and then 10,000, and it can't take 100,000, and then it breaks at some point, and then you measure the change in length. But what you find is that it's linear. So if this thing with 1 meter, how would you find the change in length? Well, to find the change in length, you would take the E max times L. You know what I mean? So that might be a good one, especially since stretch is kind of a confusing equation. So we're going to say E max times L is equal to change in length max. And that might be useful. Well, in this case, it's going to be 0.002 times 1 meter. So that's 2 millimeters. So there you go, 2 millimeters. And if I put half the max force on, it's going to go 1 millimeter. And if I put a quarter of 58,000 pounds, it's only going to stretch a half a millimeter. So it's a linear scale. And so basically at the end of the day, the take-home point is any material is a spring. For its useful, for what you want, and if you're building stuff out of wood, steel, concrete, anything, you have to work within its useful, I mean, you could get away with, building something made out of steel, some sort of hitch thing for the back of your truck, and then overloading it, and then having your hitch like bend, and then being okay with that, because now it's just in a more favorable, it's not like a cantilever is real crappy for carrying things. But if you had an angle, you know what I mean, because it already bent, heck yeah, now that can take way more load on the back of your car. But anyway, so that would be one example of where, hey, something did bend and it got stronger. And that is a concept that I have been going over in the elastoplastic problems. But at the end of the day, heck no, you want to design something where it stays within this spring, like everything is a spring. So those are the equations, and hell yeah. Alright, even though this is real small, we can still just go for it and basically find how we get this actual 33.3. You know what I mean? We can just do it with our calculator, because we already found that the change in length, you know what I mean, and it's a nonsense number, like it is 0.00 you know what I mean, 39, but that's in meters, so I can multiply by 1,000. And no, so it does. It changes 4 millimeters. So that is significant. So the change in length is 4 millimeters, but we have to use 0.0039 just to make sure all our units work. And now, let's say our question is like, hey, what's the F max? What's the force max in the cord? Well, let's use these equations. We can say that the force max is of a spring is the spring constant times the change in length. Well, we just found the change in length. We put it in our calculator, and we know that K is EA over L. So we can just easily do that. And for our problem, sorry about this. It already gives you the modulus of elasticity, and they're terrible numbers. You know what I mean? Modulus of elasticity of any material, steel, concrete, wood. That's really high numbers. This one's 2. For nylon is 2.1 times 10 to the 10 to the 9. So this is 2.1 times 10 to the 9 newtons per meter squared. That's in pascals. Write it newtons per meter squared, because then all your units will cancel. And get rid of the G, turn it into a normal number. So this is 2.1 billion newtons per meters. And then your area, it's in millimeters, but you got to convert it to meters. I'm not doing that for this one, but it's 30 divided by 10 to the 6. You know what I mean? So there you go. And so you got your area of 30 divided by 10 to the 6, and I got that stored in my calculator as 3 times 10 to the negative 5. E is 21 billion. And so now we can just plug and chug. So we can say, and I even solve for K. Now the only time you're going to get, I got hella confused with this problem, because we are just dealing with this cord, and we're dealing with the material properties of this cord, all these equations, and the length of this cord is B. So holy Toledo, this problem really messed me up, because you have this length as L, but typically for all your material property equations, you're saying the length of the thing you're actually trying to find the change in length of, or the force of, or the max stress, max PSI. So these both being L is just a real bummer. So this L is actually B, so this is EA over B. And then all these, every L in here is this length B. Has nothing to do with this length right here. All right, so let's find that force max. And it's as simple as going alpha E, alpha A divided by alpha B, and times change in length, which is x. And we got 999, so we have a force of 1,000 newtons. So that's cool, because that's a hard stop right there, because you just know something about the force that's in this nylon cord. It's 1,000 newtons. So we just dropped, and then just visually, we dropped a 2-pound mass bar, you know, with this configuration, dropped it, and we just generated 1,000 newtons. Divide by 4.44. That's 225 pounds of force in a nylon cord. Nylon's hella strong, so obviously it didn't break. And so there you go. But now the question says, what's the stress max? Well, that's just force max divided by area. So, you know, these are your gold standard equations, and I like to solve things piecewise instead of making a Mondo equation that's probably wrong in the end anyway. So we're going to take that force max and then divide by area, and hell yeah, then we get the exact answer of 33.3 megapascals. So booyah. And this might wrap up this problem, because I think figuring out like the actual velocity of this object, well, we could do that. We could do that one fairly easy. So let's do that, and that'll wrap it up. Because at the end of the day, we really wanted to figure out why the potential energy was just mgh. So let's finish the video with that. But let's go back to what the hell we just did. We had to use the more complicated form of potential energy that included this extra bit of change in length, and that changed our answer from 33.1 to 33.3. And then this answer, it might not seem like 33.3 because it's 33 megapascals. That's 33 million. So divide by 10 to the 6, and you get that 33.3. But, I mean, that's such a who cares, you know what I mean? But it was good because it was kind of like, hey, it took me a while to realize that, to be like, oh, that's what they wanted to include. And if you're taking people to the moon and stuff, you know, you might have to dot all your I's and cross your T's. But also, at the end of the day, you actually want to be in the friggin' ballpark, and so you really want to simplify. And most every problem, they even say in this textbook, is like, you don't do that. You say that the potential energy is mgh, and it's totally equal, and then the change in length of the material is just not even significant. The only reason it's significant for this 2-star problem is that it's nylon cord, and it doesn't take much strength. It doesn't take much force to really change that length. So nylon cord is definitely going to stretch way more than if this was a steel wire. If this was a steel wire, there probably would be no difference between this answer that just gets there faster than this complicated answer. And this complicated, again, it's a function of a quadratic. And so, but yeah, I do. The whole reason to do this video was to go over this quadratic equation a couple different ways, because that's a good skill to have, to be able to derive the quadratic equation besides just looking up the answer. But I mean, if you just want to, you do it exactly what I did. You throw into your calculator, you solve for 0. This x is the x in your calculator. This is your y value. And what this says is that when your y value is 0, which is this line right there, then the x value that makes this 0 is going to be your answer that solves that equation. So these are your two solutions. One is nonsensical. It's a negative x direction. And you'll get that with springs. But then the other one is a positive x direction. Because if this was a perfectly elastic and compressive spring, the spring would have a dead stop here, and then if you went the other direction, it would have a dead stop there with that same, so that is why you get a quadratic with that. But if this is a nylon cord, this problem says, hey, it can take that spring, it acts like a spring in one direction, but the second it gets past neutral, heck no, it's just a loose piece of rope. It doesn't push any compression. You know, it doesn't provide any stopping force. Because that's the other thing. The other part of these problems are like, hey, yeah, when you do let this go, max velocity, and then it goes to 0, but then you just loaded a spring, and then the spring is going to fling it back the other way. And if it's a tension and compressive spring, it's going to oscillate between these 2 points and then dampen out. But in this case, that would be a 3-star problem, and I do want to do that. I want to throw this in Excel and show that it stops here, but then the spring starts to pull it and rip it back the other direction past neutral. Now it has some velocity max, and then the only thing that slows it down is the potential energy. And this thing would have to swing up this path, so it wouldn't just be a vertical, like you know what I mean? It wouldn't just be half, but it would be very close to, if this is your change in length, the mg is just half that change in length. At the end of the day, look at that. But that's kind of more complex, but I probably will do that problem. So you can at least graph this thing in Excel to show that it does oscillate. Heck yeah. Because if all materials are springs, you know what I mean? But typically you're just loading them up. But if it's a bridge, heck yeah, cars are loading them up, and then cars are not. Cars drive on a bridge, and then they drive across the bridge, and so that bridge also does have. All right, heck yeah. So I was mentioning a bridge has cars on it and off of it, and so a bridge will flex and then rebound. And because you have motion, even in just that aspect of a bridge, you do have a velocity there, and then you have and it's damp. You know, you basically have a spring, because a bridge, when you put cars on it, wants to spring back, and when it does so, it generates a velocity and then maybe contours the other way, and then kind of acts as a perfect compression and tension spring, and then will dampen back to its original shape. Okay, cool. So what we're going to do is we're going to go over that example of that 1 kilogram block that got dropped off a 10-meter cliff. And then the reason why we want to look at this from a more fundamental approach is because the energy equation is too hand-waving. No one knows where it comes from. The energy equation says, hey, you have a potential energy that's equal to mgh, and that's this height. So this is the height, and then it has a weight of mg, and so that's the potential energy. And the second that this lands, it's going to have a kinetic energy right before hitting the water, let's say, of 1/2 mv squared. And this isn't the video to show exactly where this one comes from. Even though I probably could get there, but I'd probably make a mistake. But I definitely can tell you about this. So this problem's real easy. It says the energy initial is equal to the energy final. And now we know our inputs. We know our height. We know that we're doing a mass. And actually mass is in both these equations. So whether it's a 1 kilogram block or it's you that jumps off a 10-meter, 30-foot cliff, 40-foot cliff, what we want to know is the velocity. And so you just rearrange this equation. The 2 goes upstairs, so you got 2gh is equal to velocity squared. And then we're going to square root both sides to get square root is equal to velocity. We'll rearrange the equation. Velocity is 2gh. And for our problem, let's check out the units. Velocity is the square root of 2 times 9.81 meters per second squared times the height of 10 meters. So cool. Now be careful, because none of the units cancel, they actually add. So we're going to have, so the units on this, we're going to have 2, 9.81, 10, and then the units will be meters times meters. So we're going to have meters squared. Bottom is seconds squared. But when we take the square root of this, we're going to be left with the units of just meters per second. Cool. And so we'll get velocity is, and then use your factor of 10. Anytime doing these problems, we're going to have 10 times 10 times 2, and then square root of it. Well, I know the square root of 100 is about 10 meters per second. So we're at least going 10, and then what's the square root of 200? Well, at that point, you know what I mean, you can shut your brain off, because, or like, it might be nonsensical to guess that. Because this is a good one to do, because we have 10 times 10. Well, that's the square root of 100. But then the next jump would be 100 times 100. That would be the next sensical thing, because when we take the square root of 100 times 100. So if we take the square root of this, we get 10. So that's what that was showing. 100 times 100, the square root of that would be the square root of 10,000. And that's going to give you 100. So the square root of, so it's a logarithmic scale. So the square root of 200 is so much closer to the square root of 100 than it is to the square root of 10,000. So, I mean, we're literally, we're not going to be halfway. Oh, hell no. You know what I mean? We're not even going to be 20. You know what I mean? So I'm just going to guess 15. And I think I've already done the problem. So, but there you go. So that's using energy, and that's just 100%. You can figure out the velocity. But at the end of the day, it's just energy equations kind of sidestep everything that's going on with Newtonian physics. So we're going to do it step by step. We're going to say, hey, if this block, if we let's do the equations. So we have a weight of mg. We definitely have a force of gravity. So we're going to do the equation F equals ma. We know that this side is that Kepler equation that said, hell yeah, we're going to have a force that's mg. We're going to do the simplified version. And then we're going to have over here a mass and an observable acceleration. Because there's nothing to balance it. There's no normal force. There's no normal force that balances this. So we have an unbalanced force. And that's the other thing I should have probably gone over. Because when you cut something out, like we could even just cut this little chunk out. So we have that little chunk of beam, and now we know it has some sort of mass. You know what I mean? So or weight due to mass. So its weight is mg. It's going to be, let's say this is just 1/10 of the whole weight. So you know what I mean? So we got that. So this little m is kind of small, but then guess what? We have a cord that's pulling it up. You know what I mean? So then we have a tension in a cord, and we observe that this thing ain't moving once it's in this location, just resting, and so we know that these forces are balanced. So then we don't have any acceleration. So this little molecule isn't moving across the universe. But in our case, it is moving across the universe. It's going in that direction with this. So I'm going to be done with that setup, and we're going to go back to this one. So now we can figure out what that acceleration is. You know what I mean? So then we can cross this out and cross this out. So don't get confused with this A, because this A is the acceleration of the object. We're going to say, hey, this is our object. You know, put a 1 right here. But now rearrange the equation. The acceleration of that is g. Cool. And so here is where you would you would say, like, well, what the hell is acceleration? Well, acceleration is, I'm just going to say, change in velocity divided by change in time. I would write this a bunch of different ways. Also, like caret, I'm just going to call that caret. You know, caret V, caret T. There you go. Some people call this delta. I think delta is this, and I'm just going to call that caret. But I might be wrong. I don't know what the hell this is in Greek symbol. It probably is just a delta. Don't know. No, it is. It's a different term. I've heard his physics teachers calls this what it's actually, and I don't like that. Just call it caret. Anyway, or change in. Just say change in velocity, change in time. But this is where you get the equation dv dt. You know what I mean? Now you're doing calculus and your head explodes. But no, all this is saying is change in velocity divided by change in time. And then that's going to be, that's the definition of acceleration. Acceleration definitionally is change in velocity, change in time. Change in v, change in t. dv dt. So this is, in our place, this is going to be equal to g. Cool. Now don't get confused, because let's write this over here. We're going to have dv dt is equal to g. Now you can rearrange this. You have three elements to an equation that you can rearrange any way you want. You know what I mean? So let's say you want to find dv. Well, that's going to be g dt. What the hell does this mean? This says, what is the actual change in velocity? Maybe that's what we want to know. So the second that block steps off the cliff, or you step off the cliff, we want to know your change in velocity. And so we get that by taking that 9.8 meters per second squared and multiplying it by some sort of change in time. Well, let's just say, I don't know, 1 second. Holy Toledo. Okay, so now your change in velocity is going to be 9.8 meters per second. Cool. And so that was, but that took 1 second. Now the question is, where the hell are you in 1 second? Well, now you have to, oh, all right, my camera, I didn't set my timer, but we just caught it. You know what I mean? My camera shut off right here, but we only added a couple more things. So, hell yeah. So we just said in 1 second we're going to be going 9.8 meters per second. Cool. But now we need to know, like, where the hell are we? Because we jumped off a 10-meter cliff, so we need to figure that out. So now we know that our velocity initial is 0, so cool. And what we found, we had an equation for change in velocity. It said whatever our velocity was, it's going to change in 1 second by 9.8 meters per second. You know what I mean? So our velocity, so I wrote down velocity at t is equal to 1 second is going to be 9.8 meters per second. And this equation is velocity final is just like hell. Whatever your initial velocity was, plus the change in velocity. Cool. And again, this change in velocity comes from the definition of what acceleration is. All right, let's keep going with it, because now we know our velocity initial was 0, and now a velocity at 1 second is 9.8 meters per second. So now this is what I was getting at. This is such a fundamental, this comes up so much in physics, and especially material mechanics. You know, treating this like a spring, if you put no weight on this spring, it's going to not change in length at all. You put 1 pound on it, it's going to have a small change in length. You put 1,000 pounds on it, it's going to have a visual change in length. If your problem says P is 1,000 pounds, the question is, what was the force it took to actually set that 1,000 pounds? Well, you're not just going to put an instantaneous 1,000 pounds. You're going to start with 1, and then 10, and then 100, and then slowly build up to 1,000. And in that process, the average force to do that, well, you started with a force of 0, ended with a force of 1,000. So, like, your average force was 500. You know what I mean? That doesn't mean that's what the spring is feeling. If you have a problem that says, hey, you got 1,000 pounds on it, no, the spring feels 1,000. But the force to get up to that 1,000 pounds, you went from 0 to 1,000. So for an energy equation, we're going to say U is energy. And you might see this. You might see that energy is force times distance. Well, and it might be the integration, the vector force dotted with the distance. I don't know if it's a dot product. I think it's, yeah, it is a dot product because two vectors dot product to make a scalar. Energy is just a scalar product. But anyway, and in this case, if you had a constant force of 1,000 over that change in length, then you would have 1,000 times that change in length. But you don't. You have zero force to get nowhere, 1 pound to get a little bit, 10 pounds to get farther, 100 pounds to get not quite, very far, and then 1,000 pounds to finish it off. But your average force, your force average is what's going to be used for an energy. Because energy is how much force per distance. So you're gonna, it's a summation game. It's calculus. You're gonna take a tiny force times a tiny difference. You know what I mean? And then that's gonna be your force times your tiny force times tiny distance. And then your next thing is going to be whatever force it took to go the next part of the distance. So the force average, but it's a linear relationship, with springs, so it just makes it easy. But you'll see this a lot. You'll see like P divided by 2 delta. You know what I mean? Well, that's where that comes from. It's saying, yeah, your problem has a P of 1,000, but you're going to divide it by 2. Why? Because we want that average force and then multiplied by that distance that you see it changed in length. That's going to be the energy. Same thing here, it's just a little bit different. The question is, because this is not a simple question. There are so many times where I don't like this physics book that's like, hey, physics taught easy. It seems like it always presents 2 doors, you know what I mean? And then it asks you which door to go through. Well, by the end of it, you're never going to have a general idea of what the hell's going on. You're going to mess up 50% of the time. You're going to be like, oh, hell no. Oh, that's a little door smiley face guy. So in this, the question is, how far did you travel down the cliff? You need your average velocity. You need to say, hey, let's say I was just driving in a car down the cliff at 10 miles per hour. You know what I mean? Well, and I drove for an hour down the cliff. I'd be 10 miles down this cliff. You know what I mean? Blah, blah, blah. Obviously, that's not to scale. But here, so your average velocity. And this is so surprising that this equation isn't taught more, but it's just that number plus this number divided by 2, 9.8, and that might make sense. It seems like it's just this number divided by 2, but we'll get into from the next 1 second. It's going to be this number plus the other number divided by 2. That'll be the average velocity between the next 2 values. So do that, divide by 2, and you get 4.9. So that's your velocity average, 4.9 meters per second. And cool. So now we have another equation. So this whole process started with the equation of acceleration is change in velocity, change in time. And I would write it like this, but you could write it dv dt. I think this is a little bit trickier because this is just change in velocity times g change in t. So now we have velocity, and we want to know what the hell velocity is. Well, velocity is just change in position, change in time, or dx dt. So now we can rearrange this. And let's do it in the more complicated way. You know what I mean? We'll go v dx dt just to show you that, hey, there's nothing crazy going on here. Circle your 3 terms, and you can rearrange this equation however you want. Play around with it. But what it's saying is like, hey, dx is v times dt, and it's saying change in x is v times change in t. So if we know our change in t and we know our velocity, we can find our change in x. So that's exactly what we're going to do. We know our velocity, and this has to be velocity average. That's the only constraint, because acceleration is just average for. Acceleration is a constant for gravity, but let's say it wasn't. It doesn't matter. You're just taking small chunks. You're saying in this 1 second. If I'm trying to do a rocket equation and it says my acceleration at some point upon boost off is 10 or 9.8. You know what I mean? At some point your acceleration is only 9.8. Meters per second. And then the question is like, hey, what's going to be the velocity after 1 second? Well, I'm going to say acceleration is change in velocity, change in t, and then I'm going to be like, well, I know seconds and I know acceleration and I want to find the velocity. So I rearrange that. I'm going to say, hey, my change in velocity is going to be the number that I got, acceleration, times change in t of 1 second. And as long as you take like 1 second increments, you know what I mean? You're doing calculus, and let's continue on. I think that was a complete thought. I think you understand that. So we're going to come out over here back to change in position. Cool. It's just velocity at, that's what, because it has to be velocity average. You know what I mean? Even though this went from 9.8 to 11.8, if it's a rocket blasting off at some point, you just have to say, hey, I can only take one snapshot. I'm just trying to guesstimate. You know what I mean? I'm not going to do an integration. I'm just going to say, hey, it's that, and for the next second, I'm just going to assume that it's an average. And then I'm going to change the velocity. And then I'm going to change the position. But then during the next position, I'm going to say, hey, now this is my acceleration. So now for the next 1 second, my change in velocity is going to be higher. So that I think you see. Alright, so coming back here, change in velocity is 4.9 meters per second, and our change in time, we're just going to do 1 second at a time. And so our change in position is 4.9 meters. Cool. Now is that the cliff height? Hell no. Okay, sweet. So now after 1 second, we're halfway down the cliff. Alright, booyah, booyah. So now we're just going to redo that process, and I'm only going to use that much space because we'll let you see this picture. And so we're going to say now the acceleration is still 9.8, and we know that acceleration is dv dt. Let's do the more complicated one, and we want to solve for our change in velocity. So even though this says dv dt, always just say change in velocity, change in time. Say it like this, change in velocity, change in time, because then you can use it as an equation just like we're doing. It doesn't have to be an infinitesimally small t. Like, yes, this is theoretically infinitesimally small t, and if we do say we're using a change in t of 1 second, well, basically we're using this equation. But you know what I mean? I think it's good to make these synonymous, so then you can understand the calculus that you're doing. Cool. So now we're going to rearrange the equation because we want to find that dv. dv is equal to, bring the a and then bring the change in t upstairs, dt upstairs. And we're going to say now our dv is 9.8, and we're going to do another second, 1 second. Oh, check it out. Our change in velocity is again 9.8. So this part's real easy. We're always going to be increasing 9.8, which is about 20 miles per hour. Every second you're going to go from 0 to 20 to 40 to 60 to 80 to holy hell, do I have a parachute? You know what I mean? Until you hit terminal velocity, which is around 120 meters per second. You know what I mean? But this is how many meters per second you're going. Double it and you get miles per hour, kinda. And at the end, we'll show you the conversion between meters per second, miles per hour. If you want the foreshadow, it's times 2 plus 25% tip. That's how I remember that. Anyway, all right, so our change in velocity is 9.8 meters per second. So now for this second, so after the first second, we were already going 9.8. So now velocity at time of 2 seconds, we're going twice that. So 9.8 times 2. We're going 19.6. This plus this is 19.6 meters per second. Now we need to know our position. So let's go back to our velocity equation. We're going to go velocity is dx dt. Rearrange, and we're going to say dx is v dt. Cool. But this has to be average velocity, and I think we went over that enough. Even if I'm trying to figure out one of, a rocket equation, just at any point I'm just going to say, hey, that's the acceleration. You know what I mean? Even though it's changing, but for this next second, I have to... but in this case, it's a little different. I can't just say, I could just say, hey, the velocity is 9.8. That's a terrible guess, because over this second, I'm going from 9.8 to 19.6. So for this equation, you really want to get the halfway point. And so the equation for that is the velocity average for the second is at 9.8 plus 19.6, all divided by 2. So plus 19.6 plus 9.8 divided by 2 is 14.7 meters per second. Cool. And now what the hell were we trying to find? Oh, yeah, change in position. So we're going to take that 14.7 meters per second and then multiply it by our change in time, which is 1 second. All right, cool. We're going to go 14.7 meters. So in that second, we're going to travel 14 This is dx. This is not our position at time 2. This is our change in position. Just like we were trying to find change in velocity, this is change in x. So after second 1, we were at 4.9 meters. Now we're going to be plus 14.7 for a total of 4.9 plus 14.7. Now we'll be at 19.6 meters. So our 10-meter cliff, we definitely are in the water. This would have to be a 19.6 or 20-meter cliff for us to free fall for 2 seconds. You know what I mean? So, and just keep that in mind. Any physics problem where you throw stuff off something, you know what I mean? It's definitely less than 5 seconds, you know what I mean? Unless it's something hella tall. 3 to 4 seconds is typical for some of these problems, because that's a huge distance that you're traveling, even after 4 seconds. 4 seconds might be max, but sometimes you get up to 5. I haven't come across a problem where it was 6, though. All right, so that's that. And now, well, how the hell are you going to figure out what our velocity was at impact just from doing that? Well, our velocity isn't 19.6, but it's going to be more than 9.8. You know what I mean? So now we need to figure out where we were. And maybe it's not too bad, because this looks like, we know that our velocity increases linearly. That's kind of, it seems not counterintuitive that you have our position is definitely an x squared. It's exponential, but our velocity is consistent. So if we're about 10 meters per second here and 20 here, in this third, we would take that 10 divided by 3 and then probably add it to this 9.8 plus 9.8. So I'm just going to say a good guess of our velocity on impact is 13.1 meters per second. Cool. So that was just using huge chunks of 1 second at a time. So now what we're going to do is show you what I did in Excel. So same problem, you know what I mean? We have whatever jumping off a 10-meter cliff, and our velocity initial is 0. And so what I just do is just make the time, instead of doing a 0 to 1 second interval, I just make my interval a lot smaller. And you could do this even smaller. You could go a 100th of a second and then just have all the way up to 2 seconds. And it's going to take 1.4 to hit the water. So this is kind of overall what's that showing. How to set something like this up. Your first part is just, pick a time interval and then just throw that in Excel. There's nothing fancy about that. Then I didn't even do the x thing first. I actually did the velocity first and said, well, what's my initial velocity? Well, I said that's 0. And then I wrote the acceleration graph. So Honestly, I just wrote the velocity graph, but then just moved on to acceleration. And I said, well, for gravity, this is just a constant 9.81. So I just put that in, and I just copied the number because it doesn't change. But then I used those equations, and I said that acceleration is dv dt, and then I want to find the change in velocity. So we got dv is a times dt. So this equation right here is saying, hey, it's taking this cell and multiplying it by the change in t. And what I do is I do 9.81 times, hey, and I'm going to do parentheses, and I do this 0.1 minus this cell, 0. So then when I carry this down, this equation, we'll do this. This equation says dv is acceleration, which is 9.81, times change in t, which is 2.1 minus 2. So this change in t is always 0.1. You don't have to do it that way. I mean, but there you go. I already chose a dt, or a change in t, of 0.1 seconds. All right, and that gives me my change in velocity. So then right here, when I do this velocity graph, I just say, hey, velocity initial. So this equation says this plus this cell, those two cells will give me that number. Cool. And then I can just run that down. And then because that's 100%. Acceleration is constant. dv is, well, you can see it's always the same change in v. So there you go. Our velocity goes 0. And then at 1 second, it's 9.8. And then at 2 seconds, it's 19.6. So there you go. That's 100% to accurate. But now we need to figure out, well, change in position. So that's when I did insert this x graph and said, well, our position is going to be 0 up here. And we're going to say that this is positive x, and this is our origin, 0. And then so I said our first position was 0. Let's get some more time on the clock. All right, hell yeah. All right, so to find position, I know our initial position is 0, but now how do I find the next position? Well, I need that equation from velocity. It said velocity is dx dt, rearrange and find change in x. So dx is velocity times dt. And my dt doesn't change. And then I know my, but now the question is, what is velocity? Because even right here, I have 0 to 0.98. So this equation right here has to be dx is velocity average times dt. So velocity average is saying this cell plus this cell divided by 2. So you can just see, hey, it's just 0.981 divided by 2. That's going to be velocity average. But then what's the average velocity between these? If I say, hey, this is close to 1 and this is close to 2, my average velocity would just be 1.5. So I think you can see that. What would be the equation for that, though? It would be 0.981 plus 1.962, then divide by 2, and you get 1.47. So that is the equation for that. So hell yeah. What were we doing? Yeah, we were trying to find velocity average. So this dx, you first have to get velocity average, which is add those two cells and divide by 2, and then multiply by this dt, which is 0.1. Cool. Because you might have a velocity average of, yeah, you had a velocity average of like 1.5 meters per second. Well, cool. That means in 1 second you're going to be 1.5 meters. But our dt is 0.1. So we're basically saying, nah, it's not 1.5. It's going to be 0.15 meters. So that's going to be the change, and that's what we see. We have a change in x of 0.115. We kind of skipped ahead. We were doing that one because that was the more complicated one. This velocity plus that divided by 2 is going to be, but if we do the first one, it's going to be 0.98 divided by 2 is 0.45 meters per second, and then we're going to multiply that by 0.1 seconds. You know what I mean? So this was synonymous with, hey, my velocity after 1 second is 9.81 meters per second. Then multiply by 1 second, my velocity, or if my velocity is 9.81 and I start at 0, my average velocity is going to be 0.49, basically 0.4905, and then I'm going to multiply that by 1 second. So then I would get 0.490, holy hell, 4.905 is probably that one. And then multiply that by 1 second, and I get a position of 4.9. So that is exactly what happens after, right there, 4.905. So there you go. But because you make your dt smaller, your acceleration, so this acceleration, that's cool to talk about. Acceleration, the units are 9.0 meters per second, and that's how I like to do. If you do it meters per second, you see that that's the velocity term, and this is, sorry, it's not meters per second squared. It's just 9.81 meters per second. So there's your velocity term, which changes every, interval of time. But if we're only saying our interval of time is 0.1, then our velocity only changes 0.981. You know what I mean? And that's why right there our change in velocity is 0.981. Cool. So I think that fully explains why the numbers are kind of smaller, but still are very similar, and then meet up at the big numbers. So at 1 second, yeah, 4.908, and yep, and our velocity is 9.8. Okay, so that's what dx was. Again, dx was just velocity average. Those two added together divided by 2 times the difference between the times, which is your dt. Or you could just say, hey, dt is 0.1, and then just multiply and then reference that scale, and then hit F4 and that put dollar signs on that value so it doesn't change. So when you drag down the equation, that won't change. But sometimes I just do it this way, because when I drag down the equation, the only thing I had to just put an extra time value so it didn't mess up these last ones. All right, hell yeah. And so what this does is it gives you the position. So it calculates. Oh, so let's go over that. So this was just the dx. So right there, that's our change in x. So now we're going to say, well, let's do the first one. So our change in x for the first one was our velocity average, which was the average between 0.981 and 0. We got that. And then, yeah, we get this is our next position. Or, I mean, this is our change in x. So our x is the x initial plus the change in x. You know what I mean? So the x final is x initial plus the change in x. You know what I mean? And I guess I should write those equations, because if we have acceleration is dv dt, and we rearrange this for dv is a dt, then once we find dv, we can say v final is v initial plus dv. That's basically what we're doing. And then we're doing that again by saying velocity is dx, or it's the change in position, change in time. Rearrange this. dx is velocity times dt. And then once we have the change in x, we know x final is x initial plus the dx. There you go. So that's basically what we're doing. And then you just run it all the way down. I think we've done kind of explaining this one. But you get, it doesn't come out clean, but this is going down the cliff. So we're at 8.2 meters, 9.6 meters, 11 meters. So somewhere in between 1.4 and 1.5 seconds, we hit the water. And we hit the water with a speed of somewhere between 13.7 and 14.7. So hell yeah, going back to that, our initial guess was 13.1, even just making huge segments, you know what I mean? And yeah, so that was a pretty decent guess. So that was pretty cool. All right. So that was perfect. That was perfect. And the whole reason we did that is to show that you can use Excel to actually do the problem this way. And there is tons of problems where acceleration isn't 9.81. Whether you have a rocket blasting off, whether you drop a marble in the ocean and it hits a terminal velocity pretty fast, you know what I mean, because of the water drag resistance, you know what I mean. So you have to model your acceleration as a function of position, you know what I mean. So when you do, in this scenario, your F equals ma, well, you're going to have a weight, so you're going to have mg, like downward, but then resisting. I'm just going to say this downward is the positive direction. You're going to have a resisting force that's a function, it's a constant times a function of position, and it might just be that. It might just be a constant times a function of position, and that's going to equal ma. Well, now you're just kind of a wreck, because you basically say mass dv dt, and you have to use calculus to get an equation for velocity, to get an equation for position, and they can blow up on you. Or you can just rearrange and say, whoa, just divide by m, and now we know acceleration at every position. You know what I mean? So then in Excel, you can just run from here to the bottom of the ocean. You can run 0, 1 meter, 2 meter, 3 meter, 4 meter, and then you'll calculate an acceleration. Once you calculate an acceleration, oh, well. You would definitely want to use time. Time. If you do it this way, you still have to do it exactly the way we did it. You have to run your time at smaller increments and say, when time is 0, x is 0. So you throw in 0 for time 0, and then you find your acceleration at that time. Well, it's just mg. And then the second you get to the next position, then you have to throw in that x value. But that is a classic way to solve harder physics. Alright, we're done with this one. But I'm just showing you, like, using Excel is a classic way to solve harder physics problems, where you can just get an answer. Because sometimes at the end of the day, you don't know the calculus, but you still want to know what the hell's going on, and you can just model it using Excel. Alright, so what we're going to do, and the whole point of this was to do this problem, which I guess this is my only sheet, but it has, this chord has a modulus of elasticity, we have an area, we have a length of the chord, we have a mass, length is 0.5, chord is a quarter meter, area is that, modulus of elasticity. Mass of this bar is 1 kilogram. So what we're going to do is, the whole point of this was to, or kind of my project was to just get an equation, because the problem asks us for the max stress, which is in PSI. So it wants max PSI stress of this chord, and the answer is 33.3 megapascals. Now, we got the answer, but what I want is that stress as a function of our input parameters. So I want to input a B and an L, and then output this number. And we already did that in my last video, but we didn't solve it right. We didn't incorporate, when this string stretches, a change in length, that our center of mass of our weight is going to be lower, so we get more potential energy out of it. You know what I mean? So our datum has to be 0 right here. So when it was up here, it was h. So here's the center. We're going to say that this was h, but it's going to be h plus, not the change in length, but due to geometry, the change in length divided by 2. So this problem is kind of dually hard, because they want you to incorporate this extra change in length, and it's not directly centered over this chord, but it's a proportion of this length, and obviously just with a little triangle you can see that this extra potential energy is that change in length divided by 2. Okay, hell yeah. And so we're going to go back. What we're going to do is we're going to solve the quadratic equation, because I think that's what we're going to do first. Yeah. So let's run through this, because for our energy equation, we're going to say potential energy up here is mgh plus that, that extra. So we're going to say mgh plus delta L divided by 2. That potential energy has to equal the energy in the spring. So we're not going to figure out we don't have to say potential energy is equal to kinetic energy before spring impact, but we could do that. That's the whole reason that whoa. Yeah. Do we need to take a second? Because the reason why I did that whole deal of the block going off the cliff was to show. I do think we need to model that. That's why I wanted to make this long video. We'll get to this in a second, probably in the next hour. But what I do want to show is model this. Is like why. Why, when this weight is downward, when it's obviously obstructed by this pin, and this mass goes in a circular arc, why is it the same as this same bar? Let's say this bar is totally sideways like this, and you drop it from that height. If you drop this bar from this height, it would have the same velocity. The center of mass would have the same velocity, just as this bar, the center of mass of this bar, will have the same velocity. And there's two different ways to model this, but the simplest way, let's do it. We're gonna do this angle, and the center of it's right there. And what we're gonna show is that if here's the downward component of the weight, the whole thing was due to that energy equation. So energy is force times distance. But guess what? And for a block, hell yeah. You know what I mean? A block in midair that has a drop from a height. Well, yeah, the force is going to be gravity. So force is mg. And then the distance is just the height. So the energy is just going to be mgh. Very simple. But what gives here? Well, you got to do is calculus. And you were still using calculus here. You were saying that, hey, for half the height, chop this up into a couple pieces. You were saying that you were going mg, that was going to be your force, and you're going to move it half the height, h divided by 2. Once you get to halfway, then you're going to say, well, let's reassess, and we're going to say, okay, there's still a force on this block of mg, and the distance that we're going to travel is half the height. Cool, and that's how we get mgh. And you could divvy it up again, and you would get mgh divided by 4, blah, 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 blah. But in this case, we're going to do the same thing. So I think, what was our angle on this one? Alpha. Yeah, it was 69. You know what I mean? So there you go. So we got to do a better picture. But yeah, kind of 69 is like up like that. And then here's the center. And then we have a weight down. And if this is 69.11, sometimes it's easier just to do like the Zorro, because now you can do, 69.11. So I at least know that one. And then I know that this is a 90. So then I can say if this is theta, I'm just going to call this phi. But I know that phi is 90 minus 69.11. And we can do that, 90 minus theta. And we're going to store that as z. And that's going to be 20.89. So this angle is 20.89. And this is the weight. And then we have the path. Now, if we do have a pin here, this thing is like all velocity when rotation. Like your velocity is tangential. Like there's your, I guess the path is tangent. So the second this thing moves, it's moving perpendicular to the rotational point. So there you go. So our distance is this direction. And because energy is the vector force dotted with the distance force, the dot product is like, hey, the shadow of it. You know what I mean? If I have my force that way and my distance is this way, cool. You just multiply the two together. But if I have the force that way and then the distance is that way, well, that's at a 90-degree angle, and there's no component. This is all up and this is all over, and then so that this is just a zero value. So you have to have some sort of, so we'll just draw a little triangle here. And so this weight, this portion of this weight is in that direction. And whenever you do like vectors and triangles, just guess, you know what I mean? So if I say this is 10, like pounds, let's say it's just 10 pounds, hey, that looks like about 5 pounds. Cool. And if I say this is 10 pounds in length, the length of this, well, that looks about like 8 or 9 pounds, you know what I mean? And that's classically what we'll get. Because, and this might be like, no, I just have it kind of drawn too big. This might be like 4 pounds. Okay, and let's figure that out. Because if, oh, and then if this is, so we figured out that we did the Zorro to get this angle. We knew that this was 90. We got this opposite angle. I'm going to call that phi because this is theta. But then we do have a 90 here. So booyah, there's our theta. So there's our 69.1. And if we do the sun is shining on this, here's our vector, or W is our bigger number. Sun is shining on the sine, so we know that this is the sine component. What we want to know is the component in the direction of the distance. So we want to know the cosine. So we're going to take W cosine theta. And hell yeah. And what's cosine theta? Cosine theta is 0.34356. And then multiply by a weight of 10, hell yeah, you'd get 3.6 pounds. So we were off on our guess. It wasn't 5, it wasn't 4, it was 3.6. Let's do this other one, though. Sine theta. That's going to be 0.934. So we were pretty close to 8, 9 pounds. You know, just visually. All right, there we go. All right, hell yeah. So, but what we have here is the component of this weight force in the direction that the thing is actually going to move is just going to be W cosine theta at that point. So initially, our acceleration, what was that? That's the force. So we have to go back to Newton. Newton says force is equal to mass times acceleration. And, And this is perfect because this weight is going to have a component down the bar that is normal to this pin. The component of the weight down the bar, well, is just pushing weight on the pin. But the component that's perpendicular isn't pushing, has no resistance to it. So we're going to say that force in that direction is equal to mass times acceleration. That we are going to see acceleration because we have this force, W cosine theta is equal to the mass times the acceleration of that bar. There is no other force restricting it. If we do this component, hell yeah, this pin's got a normal force that's preventing this bar. And if we do our free body diagram, this bar isn't traveling through space that way. You know what I mean? Because this pin is preventing that. But the pin is, from this position, traveling through space tangent right there. Okay, so now we can rearrange this equation and say theta, and weight is mg, so we got mg cosine theta is equal to mass times acceleration. Mass is on both sides, and now we have g cosine theta is equal to acceleration. Rearrange that, we have the acceleration, kind of even from the initial position, is g cosine theta. And we already said that cosine theta was acceleration is 0.36 g. You know what I mean? So even just right there, this thing isn't going to fall out of the sky like someone jumping off a cliff. It's a third of that. So right initially, it's going to be a third of that. Cool. Now let's solve for at the bottom. So at the bottom, when it's at the bottom, our gravity before it hits the string, our weight force, and our distance are in the same position. So we're going to use F equals ma. We're going to say F equals ma. The weight is equal to mass times acceleration, and mg is equal to ma. So our acceleration is just going to be g. You know what I mean? Right there, we did it. We found the acceleration as g. Okay, hell yeah. So, we got to back up. Yeah, that's the acceleration. We could figure out how fast it's moving, and maybe we should do that first. I think it's easiest to figure out how fast it's moving compared to how much, what's the energy equation. So, yeah, let's do that. So we're going to say, and then doing simple calculus is doing this. It's like divvying up into two segments. Whenever you're doing calculus and you're like, oh, I got to divvy it up into a bunch of segments. Nah, divvy it up into two. You could even divvy it up in one. You can say like, hey, if this is going to have an acceleration of 0.6, what's the velocity as it travels through this arc? Now, that the only other part of this equation is that the distance of travel is the whole arc length. You know what I mean? So now we need to figure out how to figure out arc length. And how I do it is, how the hell do I do it? Yeah, you have to, I would go to radians. You know what I mean? You have to go, anytime you're trying to find arc length, think radians and how that, because I do this equation where it's like, what the hell's a radian? And a radian is just an angle. You'd be like, hey, that angle is in units of radians. And then so I use this axiom. Radians times radius is something normal. And in this case, the something normal is arc length. Hey, that makes sense. If I take something bizarre like radians and multiply by the radius, hell yeah, I'll get arc length. That's a visual, tangible thing to measure, observe, and find out about something. Okay, sweet. So I'm going to say, and then, but I don't know what the angle in radians is. Alright, hell yeah. So I had to cool my camera and we're back at it. And so we're trying to find the arc length and we're using radians. Radians times radius is something normal, it's the arc length. Anytime you're trying to do radians or arc length, you know what I mean, make it super simple, because we know that the circumference, I wish there was a better letter for circumference of a circle. It doesn't, but anyway, circumference is just pi times diameter. You know what I mean? Or it's 2 pi times the radius, because the radius is kind of what we got to work with. This whole length is 0.5 meters, so the radius is 0.25 meters. Cool. So if we, let's see what we got going. Yep, so if we have 2 pi times 0.25 meters, we're gonna get the circumference of a full circle, and it's gonna be 2 pi times 0.25. And so we would have a full circle of 1.57 meters. Now, how much of a circle is 60 degrees? Well, it's going to be divide by 6. So just mental math. If it's 90, it's divided by 4. If it's 60, it's divided by 6. So basically, our arc length right there is going to be 0.26 meters. Now, is that going to check out? Because our height, we've solved this problem, and our height was 0.2 meters. So yeah, this arc length is going to be 0.26 meters. So there you go. We're going to be going on a farther path than just straight down. So now we can use that basic calculus. And if we want the answer exactly, let's go back to this. So we wanted to convert 69.11 degrees to radians. And so we're going to say, hey, 69.1 degrees, well, there's 360 degrees in a circle, and 1 full circle is 2 pi radians. Now why is that? We've got to draw a circle here, and it's just good to know that 1 radian is about 60 degrees. So we have 60 degrees there, 60 degrees there. Now what a radian is visualize this radius right here. If you took that length and turned and made it a string, you could drape that string around the circle to about there, to about 57 point, what is it, 14 degrees? Let's see, let's see, 1 radian, we would go 2 pi radians in 360. So how many degrees, this is how many degrees is in a radian. So you go 1 times 3, or 1 divided by 2 pi times 360. So you'd have 57.229, or 57.3 degrees in 1 radius. About 60 degrees, you know what I mean? But it's not going to be quite 60 degrees, so by the time you get around the circle, it's not 6 radians, it's 6.228 radians. And 3.14 is pi, and then double that, 6.28. So that number, see how it's just like, hey, double 4 is 8, double 1 is 2, double 3 is 6. So 6.28, you'll probably see that a lot just as representing 2 pi. All right, so let's do this. Degrees cancel, and then we're just left with radians. So here's our degrees times 2 pi divided by 360. So we get a radius, or an arc length of 1.2. Oh, this is radians. Yeah, we get an arc length of 1.2 2 radians. So that's the radians. Now, that's 69 degrees to radians. So now we take radians multiplied by the radius, which is 0.25 times 0.25, and we get the arc length of 0.3015. Now, how did we mess this up? Because what did we do? Here we just guessed. That it was a full circle and then divide by 4, but that's not the case. It's going to be circumference is 2 pi times 0.25, but then we have to, that's going to be for a full circle, so we got to go 360 degrees divided by 69.11, so a little ratio. So we have 69.11 degrees, full circle is this circumference. So let's see that, and let's see if we can back up our answer. So we got 2 pi times 0.25 times the degrees divided by 360. Yep, and we get 0.3. We get the same answer. So guessing it was 60 degrees was not good because it was 70. It's about 70 degrees. Okay, but hell yeah. So there you go. So then our arc length is 0.3, basically about 0.3 meters. It's not 0.2, it's 0.3 meters. So that's significant. Now how the hell do we find, let's get a new sheet of paper. So we're going to have that distance is 0.2 meters. If we go in a radius, that's going to be 0.3015 meters. There you go. And we found out that right there we were going to get our G, our weight was down. The component in that direction was so this theta. How does that work out? A little Zorro, that's theta, that's phi, and then that must be theta. Cool. Yep, so we're going to get, so the weight component that's in the direction of the path is, so mg cosine theta, that's the force that's in the direction of the path. And that's equal to mass times acceleration. So we can find that acceleration. We already did that. Acceleration is g cosine theta, and that was g cosine theta. That was acceleration is. Oh no. What did we want? We wanted the force. Oh, no, we were right. We were right. We were just saying cosine was 0.36 g. So there you go. We just solved it right there. But and then the acceleration of gravity right there is going to be 1 g. That's going to be the acceleration. Okay, so now we need to so we're just going to, this is probably a real crappy way to guess, but we're going to say, hey, the acceleration right here to here is 0.36 g, which is, I don't know. And then the acceleration from here to here is going to be 1 g. Or what we really could do is just say, hey, what's the average acceleration? If the acceleration initial is 0.3 g and the acceleration final is 1 g, then the acceleration average is going to be 0.36 g plus 1 g divided by 2. So it's 1.36 divided by 2. 1.36, well, we can do it cosine theta plus 1 divided by 2. I'm going to store that as W in my calculator. And then so we're going to get, our acceleration is going to be 0.678 g. Okay, and it's going to be over that arc length of 0.3015, which I should have stored in my calculator too, but we can always just, with calculators, you can go back up and get it. All right, we're going to, no, we're still good on time. All right, so we're going to store that, and I'm just going to store that as x. So the arc length is x, and perfect. So now we didn't show this with the brick going off the cliff. So maybe we should go back to that 10 meters. But there's a real simple way to do this. Acceleration is 9.8. So you would say that the acceleration is 9.8. And we know that acceleration is dv dt. So then what we would do is just rearrange the equation. So then we would have dv is equal to 9.8 dt. And then we can integrate, you know what I mean? So, and then you're going to get v is 9.8 t plus c. Cool. So for every second, that's going to be the velocity in 1 second. And then c... All right, heck yeah. Now I'm not going to get too into detail in the integration. One, because I'm not 100% with the integration. I just know how this works and be like, okay, cool. That's why I do it in segments and then do it this way and make sure they make sense to me. But this says that the velocity, if we put in time 0, what's our velocity? Well, we already know our velocity is 0 at time 0. So c is 0. So that's the constant integration is no more. And then we can do this again. We can say velocity is dx dt, and that's going to equal, well, we already got an equation, 9.8 t. We can rearrange variables, and we can go dx is 9.8 t dt. Integrate both sides, we get x is 4.9 t squared plus c. We know our position at time 0. If we throw in 0 right there, we know our position is 0. So we can say, hey, that constant integration is 0. That's how to do that real fast. And so booyah. So even in here, we could be like, well, I know 10 meters, so I can throw in 10 meters right here is 4.9 t squared. I can solve for time. Or just rearrange this equation and go time is going to be x divided by 4.9 square root that. And then we're going to throw in 10 there. So we're going to go 10 divided by 4.9 square root that. That's going to be alpha t. And that's 100% accurate because our time was going to be 1.4 seconds. There you go, 1.4 seconds. And once we know our time, we can go back to our velocity equation. So I'm going to store that as alpha t. Yeah, I already did that. And go 9.8 alpha t. And we get 14. So our velocity is 14 meters per second. So booyah, booyah. And that was using acceleration of 9.8. This one I used 9.81, but there you go. And the acceleration, the velocity was supposed to be in between 13.7 and 14.7. And there you go. And a little bit closer to 13. So yeah, it was 14. So heck yeah, right on the money. Okay, so we can do that same process with this. We can say, hey, our average acceleration is, so our acceleration is dv dt, and then we can rearrange variables, and that's going to be 0.678 g. So we can go dv is 0.678 g dt. Integrate both sides. We're going to have velocity is 0.678 gt. Our velocity before we dropped it is 0. So if we do the constant of integration, at 0 time our velocity, so at t0 our position is 0, our velocity is 0. So you throw in 0 there, our velocity has to equal to 0, so our constant 0. Cool. And then we'll do this. We'll go d at v is dx dt, and that's 0.678 gt. Rearrange variables, bring the t upstairs, integrate, and you get x is, and we'll slow down on this one. We'll go, what's the integration of 0.678 gt dt? Well, make this t to the 1, and then the integration is 0.678. It's t to the exponent plus 1, so it's 1 plus 1, and then divided by 1 plus 1. So that's where you get 0.678 gt squared divided by 2. Cool. And we get oh yeah, this was w. So we stored that as w, so alpha w divided by 2. I'm going to store that as alpha v. Cool. So we get position as 0.339 t squared, and plus a constant of integration. But when we throw in 0 right here, our position is 0. So this needs to be 0. Cool. And now we can say, what's our time? We can do that same thing. We need to throw in a position of the arc length, which is 0.3015, and then find t. So alpha v is this number. In my calculator, that's alpha v. This is alpha x. So we're going to go alpha x divided by alpha v, and then square root it. So there we go. X divided by v, square root that, and we get our time. Store that as alpha t. And now we can throw in our velocity. This is going to give us our velocity at that point, and we'll see how accurate it is. It's just a guess because we only took our initial velocity and our final velocity and averaged it. It's not a linear relationship, but it gets us there. So throw in that t into this equation. So this is stored as alpha w. So we have oh, my bad. No. We have g here too. So this is going to be I did not see that. So this is going to be 0.339 g, and then you're going to have x divided by vg. So there you go. X divided by alpha v divided by g. Square root that. There's our time. Yeah, that's more realistic. It's going to take 1/3 of a second to drop to there. I'm glad I caught that mistake, and we're going to throw that into here. So this is going to be alpha w, alpha g, in our calculator, alpha t, and then we're just good to go. So alpha w, alpha g, alpha t, and we get a velocity of 2 meters per second. Cool. Now we're gonna go back and just throw in our energy equation. Potential energy is mgh, and our h is 0.2, and our kinetic energy here is 1/2 mv squared. So those two are going to be equal. So mg 0.2 is equal to 1/2 mv squared, and masses cancel, and then we got 2g.2. Square root that is equal to our velocity. So let's throw this in. 2 alpha g 0.2 square root that, and hell yeah, we get a velocity of 1.98. So this is almost 100%. This is 100% accurate, the energy equation, and this was just averaging our accelerations at initial and final. Now, it's definitely not going to make sense. Well, no, if this was vertical, yeah, our acceleration is going to be 0. You know what I mean? And then you're going to average it, get the half, and then, you know what I mean? And you can do this. You can cut this into as many segments as you want. You know, you could do something like this in Excel and cut it into at least 10 or more segments, and then follow that. Cool. But I think that gives you, that kind of proves the energy equation is based on, you know, the average acceleration over the path. Or this equation, the acceleration is not constant. It starts out small. Here it would start out nothing, but you would have to give it a little bit of an angle, and then it would start out tiny, your acceleration, and then your acceleration would be 1 gravity, 9.8 right here. All right, hell yeah. So I think that covers it. This kind of proves, one way to prove why if you have a bar on a pivot, you find the center of mass, and its potential energy is just the height, because you're not inducing any friction, or even if you did, even if this pin had friction, your potential energy is still up there. And let's say you did get down to this point, well, it would be potential energy minus that friction energy would be equal to the kinetic energy. You know what I mean? If there's an output, if that energy is being transferred to heat or some other source or air molecules, but this potential energy is still the center of mass of an object, you know, is its potential energy, no matter if it's touching or connected to something else. So it's kind of fascinating, but definitely that's the path of that object. So when you calculate acceleration and velocity and position, your position is along the path of the center of mass. All right, hell yeah. So we are going to finish this video by going back and getting that monster equation that relates. I mean, at the end of the day, we want an equation that relates right here. So we want an equation that relates the stress, and it's essentially we want the max force. You know, that makes more sense. We want the max force with given any B and L. And in the previous video, I said B. You know what I mean? If this thing was vertical. Oh, well, it's my camera cut out. But in the previous video, I was saying that if this bar was vertical, your length of the string could be as long as L, and then here's the ceiling, you know, and then you could drop it, and it would still swing down and drop, and then the shortest string could be just really short, and then. You know, so then I said, well, you want a relation. B and L could be any size, but you really kind of want a relationship between B and L. So if you choose a length, so B over L could be, well, B could be equal to L. So B over L could be equal to 1. Definitely less than or equal to 1, but B has to be of some sort of height, so it has to be greater than 0. And then so given those parameters, then we can... so inputting any L and any B, then you can output whatever the force max is in the string, and essentially the force max of the string after it impacts divided by the area is the stress. And all mechanical engineering problems, they really want the stress, just because that's for any material, like we said, there's a stress max. That's the breaking point, you know, of the material, or that's the point where it's no longer elastic. That's the point that, as an engineer, you don't want to hit. You always want to design for inside that. But heck yeah, that's a universal PSI. Every molecule of this nylon cord can only take, you know, let's say 60 megapascals, and then we're hitting 33.3 megapascals. So maybe that's kind of what the problem is. I actually haven't figured out what the max force is, but we could say, hey, strength is force over area, and strain or stretch is change in length over length, and we know that strength is strain times E. So heck yeah. So we need to know. Can we know do we have enough information? I don't think so. I think you have to know what the tensile strength. You have to know the tensile strength. Like between these three, you need to know two. So that's a good thing to bring up, because material mechanics, these are your three equations. You know what I mean? And typically, little bug. Typically, what they will give you is modulus of elasticity, and that's cool because. And then from the books, you should be able to look up a nylon cord or steel and find out its tensile strength or compressive strength or whatever you're trying to do with it. Typically, tensile strength, and then you can rearrange that equation and find the stretch. But yeah, most problems won't give you the strain, you know what I mean, the max strain of the material, and that's kind of frustrating. Even though they will give you the max stress, they'll give you like the yield stress or the ultimate stress with a U. That's given. But just know that if you have the modulus of elasticity and the yield stress, you know what I mean, and whatever their label they're putting on this, you know what I mean, I just like to think of it as like the braking stress, but that's not quite right, you know what I mean? Even though your graph does go like this, and for elastoplastics, once you get to this yield stress, well, that's the same stress that breaks it. You know, you just have like some doughiness to it before it does break. But sometimes you don't get extra strength. But steel you do. You get strain hardening, so you get extra strength out of it. That's why you get this ultimate stress in PSI. But at the end of the day, they're not going to give you the strain value, the max strain and I guess this could be yield strain. So whatever substrip you're going to put on stress. Am I saying that right? Because I call it strength, but stress, whatever substrip. So if you're saying the yield stress is equal to the yield strain times the modulus. So E is the only thing that's a total constant because it's the slope of this line. And this line is a linear. So every material acts as a linear spring up to the point where you lose your job or people lose your lives. You know what I mean? You don't want to pass that for most structures. You want to be below yield by a factor of safety. But yeah, so you could say, or the ultimate stress is equal to the ultimate strain times E, or the max stress is equal to the max strain times E. And then whatever label, you can just put your labels on, because now you can see max force or max change in length. But the other parameters that are given are length are already given. This is going to be your initial length, your initial area, and then keep that in mind, because as things stretch, they not only get longer, but they also get narrower. But the spring equation is based on initial lengths. So you have to think of these material mechanics equations as basically a spring oriented. Like this length is initial length. This area is initial area. Those initial parameters, once given, stay the same. You know what I mean? Just because the force of a spring is K change in length. And that's F EA divided by L change in length. So your change in length will lengthen, but you still keep the initial length. And a change in length due to Poisson's ratio, things will get longer, but then also skinnier. So your area will change. But this is your initial area, and then E is constant. So that's just a good thing to go over before we're going to print out some more sheets of paper. And hell yeah, what we are going to do is we are going to get an equation of that stress as a function of L and B input parameters. And we're going to do it where, once this bar and changes length down there, we're gonna add that extra. So the potential energy is this height plus change in length change in length divided by 2, because that's change in length. It's a triangle, change in length divided by 2. All right, let's do that monster. And in that process, so what we're going to be doing is we're going to be going over the quadratic equation, and we're going to solve the quadratic equation as a proof. So that's always fun to do. Never look up the quadratic equation, because if you solve it as a proof, we'll get to it, but you get a different form, and then you can use that form to check the actual form online. You know what I mean? If I have to rattle it off, it's well, what the hell is it? Negative b plus or minus the square root of b squared minus 4ac divided by 2a. But you could mess that up. You know what I mean? I've done this enough, and I don't even memorize it. What I think is like, well, one of these b's is negative, and it makes sense that this b is negative, and always a plus and minus in front of the square root. That's just intuitive. But this is never a negative b square root. That would just be... Seems nonsensical to square something and then make it negative, and it runs into the issue of like, well, is it like this or it's like that? So just that's one way where I can just be like, hell no, there is no negative in here, and it's just b squared. But it is negative 4ac. I definitely remember that part. It's just not negative b squared minus 4ac. For whatever reason, I can remember that. But hella negatives in here, you know what I mean? So you definitely have that negative b. Don't forget that negative. All divided by 2a. I think everyone can remember that part. All right, so let's throw some more time on the clock, print out some more sheets, and let's do the quadratic equation. Once we do that, we'll go back and do the radius of this to find just all the parameters based on length and this height of the string b. Alright, hell yeah. Alright, hell yeah, let's jump in. So we have that same thing. We're going to drop it down to here, final location, change in L divided by T. Here's our height up there. So energy says potential energy is mgh plus change in L divided by T. So let's do it. So our potential energy is mgh plus change in length divided by 2. That's going to be equal to the energy that gets put into the spring. That's going to be 1/2 k d squared. And back to our strength and energy, or material mechanics problems, equations, force over area, and stretch is change in length over length. And strength is stretch times modulus of elasticity. You put those two equations together, you get FA is equal to change in length over L times E. You rearrange and you can get a lot of different things. You get change in length as FL over EA, or you can get force is equal to change in length EA over L. Those are easy. Or you can just flip this one just a little bit around, because the force of a spring is K change in length, and so this will be EAL change in length, and so hell yeah. So then K, your spring constant for any material, is EA divided by L. So those are the quick things that you want to do for any given problem, because now, hell yeah, we got K out of the way. It's EA divided by L. We haven't figured out H, you know what I mean, in the other video we did, but we'll do that dead last. We did, that's a geometry problem, you know what I mean, where actually this initial angle is equal to that angle, and so the angle final is 2 times the initial angle. But there's even a simpler way to get H as a function of L and B, the input parameters. Okay. So what we first got to do is FOIL this through. So this thing says mgh plus mg delta L divided by 2 is equal to 1/2 k. D is I'm just going to do delta L. I think change in length, this little term change in length, is just way easier visually for me for material mechanics problems than, like, using this as a delta or the spring constant D, because now we have 1/2 k change in length squared. Okay, what we want to do is rearrange and make this equation equal to 0, so it looks like a polynomial function of ax squared plus bx plus c is equal to 0. So here's and our x variable is just change in length. So here's x squared. So see that? So we're going to go 1/2 k change in length squared. And then minus, we're going to minus this side because this has the one of the other x variables. It just has change in length to a power of 1. So we got minus mg change in length. I'm just going to do I'm just going to do 1/2. Yeah, there you go. 1/2 mg change in length. And then we're going to minus this, mgh. This would be change in length to the 0 if you wanted to do that. That just makes that 1. That's kind of a fun thing to do. But anyway, so there you go. So our variable a is going to be that. A is 1/2 k. Our variable b is negative 1/2 mg. Our variable c is negative mgh. Cool. So now we can solve for our x value is change in length, right? So just like if this was a quadratic, we can solve for x. And typically you would do x is negative b squared plus or minus the square root of b squared minus 4ac divided by 2a. But let's what do you call it? Prove that that's the case. So how you do that is you start with ax squared plus bx plus c is equal to 0. And what you're trying to do is get this side of the equation to have x times x and probably a plus here, but these two terms to be the same. So then you can go x plus whatever that term is squared is equal to, now it ain't going to be equal to 0 at that point, but it's going to be equal to something. And then the whole name of the game is then square root this, square root that, and then you would have x plus something is equal to the square root of that jazz. And then you could solve for x. X is going to be this jazz minus that thing. You know what I mean? So fundamentally, that's exactly what we're doing. And so let's do it up here. So we're going to do ax squared plus bx plus c is equal to 0. Well, the first thing to do is you want no term here at all. You just want x squared. It just makes this so much. We don't want a term out in front of x. So that's step 1. So how you do that is just divide by a, divide by a, divide by a. 0 divided by a is I guess it's just the same numbers, still 0. So there you go. So now we have x squared plus b over ax plus c over a. Now the next thing is this term is not going to help us. Like right now we can't just be like, oh, I see it. X, you know what I mean, plus blah 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 squared is so this term is not helpful. So then the next thing to do is get this term to the other side. So we're going to go x squared plus b over ax. I'm still going to plus something here because we need to figure out what the hell that is. And then we're going to go equals negative ca. So now we can do our magic. So we're going to say x, you know what I mean, plus something, is going to equal just this. We're not going to worry about that side of the equation, just this. You know what I mean? And so anytime we do this, you know what I mean, the formula is like, well, and I do it different. Instead of going x squared plus, one of those and one of those, and then these two terms squared, well, we just do it x squared plus, hey, those two terms squared, and then plus 2 times x that. You know what I mean? So there you go. That's kind of the general gist. And at the end of the day, what are we doing at the end of the day? To make this work, I don't think that was very helpful. But it's just, you might just have to know this, is that let's see. Oh, to actually get this term, you're going to have to, you know what I mean? The two middle terms have to add up to that. So, well, let's try it. So, take this middle term and divide by 2. So, we're going to go b over 2a. You know what I mean? So, then throw that in there. b divided by 2a. b divided by 2a. And just see what happens. You know what I mean? Because then you're going to have x squared plus, well, we'll just do the middle term. You're going to have b over 2ax plus b over 2ax, which is equal to b over ax, which is exactly what we have. So hell yeah, hell yeah. So that term jives. And technically, so now you got that, but you still need to do this 100%, because you got x squared, you know what I mean? And then you'll have, because I like to do these terms next. Do these terms first, x squared, and then square these terms. Because then you're going to have b squared over 2 squared a squared. You know, you'll just have b over 2a squared. I should have done it like that. And then you're going to have that additive thing. You know what I mean? You're going to have basically that term, b over ax. Cool. So no one's going to do it that way. They're going to do it the other way. They're going to go x squared plus b over ax plus b over 2a squared. So now that we don't have a b over 2a squared right here. You know what I mean? And if we put b over 2a squared, we got to put plus b over 2a squared over there, which we just did. All right, hell yeah, we're back. So yeah, so you know what I mean. Once you square these two things, yeah, you don't have that term, but you do if you just add it in. But you have whatever you add on this side of the equation, you have to add over there. So now let's get it kind of a little fresher. So we're going to go x squared plus b over ax plus, and I'm gonna run this through. I'm gonna say this is b squared over 4a squared. And then I'm going to equal that to negative ca plus b squared over 4a squared. Cool. Now this side of the equation, like we said, is x plus b over 2a squared is equal to negative ca plus b squared over 4a squared. Because now we can take the square root of that side, and then once we do that, that goes away. And then you can take this to the other side, minus b over 2a, and that goes away. So hell yeah. So now we have x is equal to plus or minus, and just because you have a square root there, I think you just got to do plus or minus. You know what I mean? I'd have to do a full college lecture on what the hell. No, it just makes sense. It's your imaginary numbers. You know what I mean? You're taking care of all your bases. Okay, but that's inside that, and then minus b over 2a. So there you go. It looks nothing like x is negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. But this is the place that I would hard stop. You know what I mean? Get it to here, and now you do have two equations. And then I'll quickly show you, maybe not quickly, but how do you get this equation? How do you get this equation to look like that equation? Well, you have to get the denominators the same. So you have an a down here, but you have 4a squared over here. So you need to multiply this by 4a. And then multiply this by 4a. Oh, and now, don't you see this? This is negative 4ac. So now we're working it. And this is b squared minus 4ac. So you could rearrange those terms. And then you have in the denominator, so you can add these because your denominators are the same. And then downstairs you have 4a squared. Well, if we square root both these things, then you end up with 2a. Holy Toledo. So at the end of this, this thing's going to be divided by 2a. Guess what? That thing's divided by 2a. Holy Toledo. So inside this is b squared minus 4ac. And then outside, you know what I mean? This makes more sense to do this minus b. But now they just have to do, they have to bring the negative in front, you know what I mean? Minusing b is the same thing as minus b plus all this crap. So that's just the way they did it. They took this minus b and then put it in front and then added it. You know what I mean? So it's kind of dumb, but there you go. Then you get minus b plus or minus b squared minus 4c all over 2a. But this is what we got. We got plus or minus, I don't even know what we got anymore. But we got the square root of c divided by a plus b squared over 4a squared minus b over 2a. So, hell yeah, I'm going to write that on a new sheet of paper. So we got x is equal to plus or minus the square root of c over a plus b squared divided by 4a squared minus b divided by 2a. Alright, hell yeah. And in this case, our a, back to here, our a is 1/2 k, our b is negative 1/2 mg, and our c is negative mgh, because this is the equation that we set this equation to 0. We took this energy equation, there you go. So now we can, and then only the positive root is the one that makes sense. And, you know what I mean, you'll just have to trust me on that. But the negative root over there makes no sense. The negative root will give you a negative number, and a negative change in length is just not physically making sense. It's because it's stretched this way. The negative direction is the compression direction. The string can't take compression, but that's why you get that for a spring. It's got two different stall points. Alright, so now we can just throw it in. So we're going to go x is equal to, and we're just going to use the positive form, but we're going to go 1/2 k divided by, holy Toledo, this is c divided by a, so we'll start over. We're going to go x is equal to the square root, c is negative mgh, and divided by a, which is 1/2 k. So the 2 pops to the upstairs, and we got negative 2, and then we got divided by k. But k is EA divided by L, so let's just do that right away. So we got EA and then L, hell yeah. And then we're going to add, what's b squared? Well, that's going to be, we got negative mg divided by 2. We're going to square that. Well, we're going to get, the negative is going to go away. We're going to get mass squared, gravity squared divided by 4. Cool. And then we're going to divide by 4, and then what's a squared? Well, that's going to be, a squared is k squared divided by 4. Cool. But that k is EAL. So we're going to have e squared a squared divided by 4l squared. You know what I mean? It gets kind of confusing. But there you go. We might have to do this in a couple steps. But b squared is m squared g squared divided by 4. Divided by 4a is, well, I guess there's the 4. And then the a squared is e squared a squared, and then you got 4 up top, l squared. So one of these 4's cancels top and bottom, and that should do it there. And then you got negative b, so there's just going to be a plus, because b is mg divided by 2, but then you got 2a. We're just going to divide by 2, and then you got 2a, so that's 2, and then a is a 2 upstairs, and then a is k, so that's EAL. There you go. 2's cancel. Hell yeah. Holy Toledo. So your x is going to be square root negative 2 mghl over EA plus, yeah, this all looks good, m squared g squared l squared divided by 4e squared a squared, hell yeah, plus mgl divided by 2ea. And it's just like, holy Toledo, you probably made a mistake or something. But no, we're good. Because this is squared. So, well, I don't know. Hopefully this number is friggin' bigger, because this can't be a negative number. And then this, what the hell does x give us? Well, x is going to give us that change in length. Remember how x was change in length, and it was a quadratic? So this is your change in length. And then if we know change in length, the force of a spring is k change in length. And then so we can say force max force max is k times change in length. And k is that EA divided by L. So you take this and multiply by EA divided by L, and you'll get force max. And then sigma is actually what we want, sigma max, and that's going to be force max divided by A. So force max is EA change in length divided by L, but then we're going to divide by A. So the A's cancel, and you're going to get E change in length divided by L. So that's exactly what they want for the problem, is sigma max E change in length divided by L. And we'll have to get it to this form and throw in h of 0.2, and then we'll have to go back and solve for h as a function of L and B, and then we'll have just the one monster equation that will work out. But I swear to God, I probably made a mistake, but you never know. Alright, hell yeah. So we're almost there. So what we're going to do is we're going to take this change in length and multiply by E divided by L. So we're going to go, hey, sigma max is E divided by L, and then all that, negative 2 mghl divided by EA plus m squared g squared L squared 4 E squared A squared plus, and then this thing we would just multiply by EL. And hey, look at that, EL cancel, so this is just going to be plus mg divided by 2a. And let's try this. So in our calculator we got alpha E. That's right, alpha L. Oh, holy hell. Okay, so we probably made our... No, we haven't made any mistakes. So like I said, this L is this B. L has nothing to do with this L. But everything we've done has just been related to the spring constant, I think. Nothing, there has been no variable that has involved this length. So every L that you see and change in L is B. And it's just really hard to write your material mechanics equations and change just that classic change in L over L, like strain. You know, to change this to change in B divided by B. That's just a little bit headachy. But this is where you come into huge errors if any of your parameter, the only parameter that involves L, this length, is H, and we haven't made an equation for that. So hopefully we're still good on that. All right, alpha M is 1, alpha G is 9.81, and then alpha L. See, but here is where you can't just type in L. So sigma max right now is alpha E divided by B, square root, negative 2 mgHB divided by EA plus m squared g squared L squared divided by 4 E squared A squared plus mg divided by 2a. So these 2L, bummer, there's another b. So b squared. These b's are that. So yeah, holy Toledo. Because once we do solve for h will be a function of L and B, and it'll be this L and that B. So now in our calculator we do have alpha b as 0.25, and alpha h is stored as 0.2. Alpha a is right too. Okay, so let's do it. Let's do alpha e divided by alpha e divided by alpha b square root, and we're going to go -2 alpha m alpha g alpha h alpha b divided by alpha e divided by alpha a. So we did that, plus alpha m squared plus alpha g squared. Just multiplied. Sorry about that. So it's m squared g squared b squared. Divided by 4 divided by e squared divided by a squared. Now I'm getting used to this of just like, hey, do everything on top, but if you have stuff in the denominator, just divide by 4, divide by e squared, divide by a squared in your calculator. Then you don't have to use parentheses. And then, okay, plus mg divided by 2 divided by a. See how I did that? Okay, and hell yeah, and then enter. Yeah, and yeah, I knew I was going to get a hiccup, because this shouldn't be negative, I don't think. So we're gonna, but that's fine. We have the structure exactly what we did. We just made an error, and this happens all the time. You know what I mean? And so I'm just glad. I'm totally cool with this happening in videos. Even though you kind of start back from the drawing board of saying mgh plus mg change in length divided by 2. That's the potential energy, is equal to 1/2 EA divided by L. So that's the K. And then change in length squared. You know what I mean? Or I mean, this in general is mgh 1/2 mg change in length is equal to 1/2 K change in length squared. So we rearrange for that quadratic, and we get we get 1/2 K change in length squared minus 1/2 mg change in length minus mgh is equal to 0. Our A is 1/2 K, our B is negative 1/2 mg, and our C is negative mgh. Now remember I said if we have two equations, so we do, because we have that other one. The other form of the quadratic is a negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So we can just throw these parameters in, and let's do that. So negative b is just 1/2 mg plus or minus the square root b squared. Well, like we said, this is going to be negative mg divided by 2. If you square it, the negative goes away, and you're going to have m squared g squared divided by 4. So cool, you're going to have 1/4 m squared g squared. Cool, and then you're going to minus 4ac. This is where I got into a hiccup, because minus 4ac is plus. You know what I mean? So now we can just go back to here, and so where did we run into? So our negative. Yeah, we might have to go back just a little bit farther. Yeah, but that was minus CA, and it's minus 4AC, and so we have a minus CA. Yep, and duh. Okay, so this is minus CA, so there's our mistake. See, and this is such a I make this mistake all the time. It's very difficult not to make this mistake. This says minus CA, so let's write that. Minus, and then C, and then A. And then all we want to know is whether it's positive or negative. So we're going to go minus. C is minus, so we're going to go minus. A is positive. Cool. So we have a minus, and that's going to be a positive divided by a positive. So there you go. So this is positive. And that's it. That was the only, there was just one little error, and it was right there. This is a plus. And I'm glad I did this problem at least once to realize, yeah. So now we can just go back to our formula and just throw a plus sign. See how you just do everything with the quadratic, and you just get down to a plus sign. And with the quadratic, we would have done the same thing with here, and we could have made the same mistake. But having two different equations, that just shows that, hell yeah, and we get 100% the right answer. So hell yeah, we don't have to go back and do it again. But there you go. So our stress equation is 100% accurate. You get and you divide by 10 to the 6, because that's 33 million pascals. So you get 33.3 megapascals. That's the answer in the back of the book. But now I'm still not satisfied. What I want to do is get this H, and I think like H was just B over L plus B over L squared. I think that's what H was. But I just want to prove it one more time using, like, this sweeps out into a circle. And then also this sweeps out into a circle. So we can take the equation for this circle and the equation for that circle, make them equal to each other, and then we can find this height y. That's what it'll be. And then we know that this height, due to geometry, is just half y. So this h is just equal to y divided by 2. So that's the next thing that we're going to do. We're going to throw some more time on the clock, and let's do that. But we could have, we got 28 more seconds on this timer. We could get another equation that's like this. You know what I mean? But at the end of the day, this one is so much more maybe useful, just because you don't have everything over 2a. Like here's your plus or minus component, and then here's your other component. You know what I mean? You don't have you just don't have it kind of mixed up. Alright, hell yeah. Hopefully we can do this in 10 minutes. We probably can't, but that's about all the battery juice I got left in this battery. So what we want to do is find an equation for this circle, an equation for that. So we need the general form. I mean, the easiest form for a circle is x squared plus y squared is equal to the radius squared. I think that's the easiest one to memorize. But how do you shift a circle? You know what I mean? Because if here's our origin, 0, 0, hell yeah, that's the equation for this circle. But then if we have another circle over here, how do you have an equation for a circle with an origin over there? Well, you use this. It's going to be x minus x naught squared plus y minus y naught squared. Where this is going to be x naught y naught. Just the x and y coordinates. And guess what the x coordinate is? L. You go over L and up B. So there you go. You got LB. So then the equation for this one is x minus, well, x naught is L. So there you go. Plus y minus b squared. And these are equal to the radius, which is the radius. The radius is this string, b squared. Cool. So now what you're doing is you're setting these two equations equal to each other. When you do that, that means wherever they intersect, the x and y value that you throw in right there is going to make both these equations equal to each other. All right, so let's do that. So we have to, like, this is x minus L, x minus L. So now I'm going to show you the way I do it. I go x squared plus L squared. Those are the two squared terms. You might as well do those two terms first. X times x is x squared. Negative L times negative L is positive L squared. So it's just really easy to get those right off the bat. And now we're going to go minus, 2xl. There's a minus xl there and a minus xl there. Anytime you do squared, well, it's just this term times that term, but then two of them. Cool, and we're done. And now we can do the same thing over here. Now we're going to have y squared plus b squared. And now minus 2yb. You can just do it in any order, but it's just really fast. And that's going to be equal to b squared. Now the easiest way I thought to combine these, and this r squared, I apologize. Yeah, this was the general form, but we're going to have x squared plus y squared is equal to L squared. That's what our radius is. Booyah. So now we have an x squared and a y squared. Well, there's x squared plus y squared. So these two terms are going to equal L squared. Cool, and we're already adding to another L squared. So I can go 2L squared minus this, 2XL, minus, oh, and then right here, like, hey, there's a b on both sides, so I can just get rid of those. So then minus 2YB is equal to 0. All right, hell yeah. And now there's a 2 everywhere, so we can go L squared minus XL minus YB is equal to 0. Now, what do we want to solve for? Do we want to solve for x or do you want to solve for y? This comes up all the time because you're like, well, I do want to know y, but don't solve for it right now, because if you solve for y, you know, you would have something over here in terms of x, and then you would throw that crap into this y, to the other equation, and then you would solve for x. So to get y at the very end, you need to, you know, throw in something for x here that's in terms of y. So we're going to solve for x, and it's going to be in terms of y. So there you go. So anytime the thing that I want is negative, I'm just going to throw it to the other side. But then I do it in 2 steps. I throw it to the other side, but then start the equation with that. So I'm going to go positive XL. That means I threw the equation to the other side, but mentally these two don't change. So that's going to be equal to L squared minus YB. Cool. And now I'm going to divide by L. So x is equal to L minus, I'm going to rearrange this, B, L, Y. There you go. So this is my term for x. I throw it into the x squared. So I got to square it. So I got to do this twice. And if I do this twice, it's very helpful to write it twice. But now I do the same thing. L squared, and then square these terms. This is positive b squared L squared y squared. Did that. And now do the intermediate term. Well, there's going to be a negative, it's going to be 2, and it's going to be 1 times one of these, which L times L, that cancels, and it's just going to be by. There you go. Done and done. And we threw it into this x squared plus y squared equals L squared, so we still got to add the y squared equals L squared. So perfect. We combined the two equations. They're all combined. And we need to, hey, L squareds cancel. So now this is just equal to 0. And now we can get terms together. Like these y squared terms are way different than this y term. So we need to, you know, let's factor out the y squared, and we're going to have 1 plus b squared L squared. There you go. And then minus 2by is equal to 0. Now, you're supposed to factor out a y and do this. You're supposed to go, hey, y, and then this is going to be y 1 plus b squared L squared minus 2b. And then that's going to be equal to 0. Anytime you got a quadratic, you know what I mean? Hey, if this term is 0, like that's a solution. There you go. That's not a very helpful solution. That just shows that solution right there. I'd never even thought of that. Yeah. If this is a circle and that's a circle, obviously that's a solution. That's where these are equal. That's not the one we want. We want the one that actually is positive. But to do this, you can't just divide by y. You can't just, you know, cross out a y there. You know, if you watch some of those higher up math videos, what they do is you have to factor it out and say, hey, this. You got two equations. You have this. Like if this is equal to 0, it makes it 0. But because it's a multiple, if this side is equal to 0, then it's equal to 0. So you got two equations. One is y is equal to 0, and the other thing is this is equal to 0. So we're going to go y 1 plus b squared L squared minus 2b is equal to 0. So hell yeah, let's take the 2b to the other side just by that. And now we can divide by this. So we got y is equal to 2b divided by 1 plus b squared L squared. Cool. This gives us this full height y. We're interested in this height. You know what I mean? And only if you've done the problem multiple times, you're like, oh yeah, I'm not going to make that mistake. So this h, and we're finally in terms of b and l. This h in terms of b and l, that's the only input parameters, is going to be y divided by 2. And then just divide by 2 is those 2's cancel. So we have h H with our input parameters of B and L is B divided by 1 plus B squared L squared. Cool. And now we got that, and we can go back to our, where's our good equation? We're going to have to take a pause. Alright, hell yeah. Hopefully my camera doesn't crap out. But yeah, this was our final equation for stress. This is what they wanted in the book. And now we can throw in that parameter for H. You know what I mean? And you know, we don't have to simplify anything. And we'll get this so you can kind of see. And so hell yeah. So we have we finally know that H as a function of L and B is, what was it? It was, I guess it was right here. It was B divided by 1 plus, we'll go B over L squared. We'll write it like that. I think that's, I don't know. No, I don't like it. I don't like to write it that way. I think I'm going to write it B over 1 plus B squared L squared. It's alright if these individual terms have their own exponent. I like that kind of more. And now we're going to write this final equation. Sigma max is equal to E divided by B. Now this length is this length. You know what I mean? Finally, we have something of this equation. H was in terms of this length of this bar, so it's not B. So there you go. So we have E over B square root of 2mgh B divided by EA plus m squared G squared B squared. Ah, damn it. I forgot to put the H in. So let's think about it. If I do put the H in, this H will be B, and we'll have a B squared up top, and then we're going to divide by, I don't know if I can do it that way. Sure. But when I divide it, it'll be 1 plus B squared over L squared. All right, let's do one more time. Is equal to E divided by B, square root, 2mgh B squared divided by EA 1 plus B squared L squared. That has to be in parentheses. And now plus M squared G squared, we're right here, B squared divided by 4 E squared A squared. That's all in parentheses. Plus mg divided by 2a. Alright, hell yeah. So we did it, and now we can put this into our calculator just to make sure. So we got alpha E divided by alpha B, square root 2 alpha M alpha G alpha. How did I, you know what I mean? This H, we've already did it. You know what I mean? I didn't have to write. We already made the B up top, B squared, and then put that on the bottom. So sorry about that. A little faux pas. But we have alpha. Oh, I guess we're just starting over. Alpha E divided by alpha B, square root 2 alpha M alpha G alpha B squared divided by alpha E divided by alpha A divided by square root of 1 plus alpha B squared divided by alpha L squared. Parentheses, I don't know what the hell I said right there. Okay, so that's all on the bottom, and then we're going to go plus, alpha M squared alpha G squared alpha B squared divided by 4 divided by alpha E squared divided by alpha A squared. And that's it. That's under the square root, and then plus alpha M alpha G divided by 2 divided by alpha A. Enter. Hell yeah. So we get the right answer. So there it is. This was a culmination of a bunch of nights, you know, probably spending 3 and then 2. I think this is the third, maybe fourth time posting a video on this problem. Probably just the third time. But I'm totally done. I don't know how long that took. Probably about 3 hours. But we finally got the equation that I was satisfied with. And it's longer because I'm explaining as I go. You know what I mean? Most of these problems, it's I kind of just do a little bit and then go eat a sandwich and then come back or something. But Sometimes it's hard to do them all in one go. Sometimes it's hard. I mean, sometimes it's easy just to throw the numbers into your calculator and see if you're on the right path. But to actually put it all together, especially just working with variables, it's really easy to make mistakes. You know what I mean? Because like right now, this means nothing to me. But there are components that, yeah, it does. It means absolute garbage to me. But we could simplify it just a little bit, because we have an e. This is an e to the 1 upstairs, and then you're basically dividing by e to the negative e to the 1/2. So that's e to the 1 times e to the negative 1/2 there, and so you could factor through this, and then you would get the e upstairs. So you could, I don't want to ruin my equation, but that e would be upstairs there. But you'd have to do the same thing over here. You'd have to factor this through. So you would have an e to the wait, did I even do that right? Well, yeah, the e is outside this, so this is inside, so you'd have e to the 1 divided by the square root of e. So that's what we did there, and that's a check mark. Now this is e squared, but then it's square rooted. So hell yeah, the e just goes away on this side, because this just pops out, and then the b. The b's pop out. So we could let's throw some more time on. Well, let's see if we could do this. Let's see if we could do this. So I'm gonna get this equation just a little bit higher. Yep. See if we can simplify it. So what the hell does this mean? B squared, but the square root of it. So that's just b on the outside. And this is just b on the outside. And so guess what? Those b's cancel. So that's kind of cool and crazy at the same time. How sigma max isn't a function of b in those parameters. It's only a function of b in this parameter down there. That's fascinating. So hell yeah. So we're going to go... and then, so the b's cancel. Now this e, we want to... we already did that. The e is going to be upstairs, so we're going to do the square root of 2 mge, that's upstairs. The b's, we already mentioned what the hell happens to the b. Now it's a 1 plus b squared l squared. Hell yeah. And then plus, now this e just pops out. This doesn't even have an e in it, doesn't have a b in it. You know what I mean? So those just go away. So now we're just m squared g squared divided by 4a squared. And then we got that. And then we got plus mg divided by 2a. And you know what I mean? There's not an a squared there, so we can't pull that out of we can't make the denominators. But yeah, that's the next thing. So this should work. The other aspect is we could make these denominators the same. You know what I mean? And that's kind of tricky and fun at the same time. It's a skill that is required in a lot of math problems. So what you do have to do you have to multiply this by 4, multiply that by 4. You know, anything you do downstairs, you got to do upstairs, because that's just multiplying by 1. So now we have the 4a, but now we have to put an a squared right here, so we're going to put an a upstairs. Cool, but now you have this crap, so then you're going to have to do 1 plus b squared divided by l squared, and this might not simplify things. Okay, hell yeah. So now you can combine, not only can you combine these two equations, is that you can pull out this term altogether. So once your denominators are the same, once we pull out this is going to be all divided by 2a outside of the square root. Well, guess what? You have a 2a there. So this is going to be all divided by 2a. Cool, and you kind of have something like the quadratic. All right, more time on the clock. Alright, my camera is seriously going to run out of juice, and I'm going to be bummed, but whatever. So we're going to have 8 MGEA plus m squared g squared 1 plus b squared l squared. See, it doesn't make it any nicer, because then on this downstairs you have 1 plus b squared l squared. So yeah, that's not super friendly looking at all. But then you're just going to have plus mg, but then you're going to divide by 2a. So that sucked, and I hated it, but it was probably correct. And so let's get the other one that we thought was fairly decent. And well, let's go back to this one, because I think the form that I want is just a little bit cleaned up, but it was reminiscent of this one. So we're going to have the square root of 2mg. That's it. And then mge. There you go. 2mge divided by a 1 plus b squared l squared. So we still didn't even figure out if this worked in our calculator, but m squared g squared divided by, and this was just 4a squared. Cool. Plus mg divided by 2a. So there you go. That's cleaned up as I would ever want it. So we're going to do square root 2 alpha m alpha g alpha e divided by alpha a divided by the square root of, I'm still calling that the square, this the parentheses. 1 alpha b squared divided by alpha l squared. End parentheses. Whoop. End parentheses plus alpha m squared alpha g squared divided by 4 alpha a squared. Cool, did it. No. It's divide by 4 divided by a squared. You know what I mean? I kind of like this trick. I don't know if it's a trick. It just kind of makes things simpler, but you got... Alright, holy Toledo. Alright, so we got a new battery. We can kind of slow down and finish this one up. So, let's see. Did we get it right? Divided by 4 divided by alpha a squared. What the hell is that? Square root plus alpha m alpha g divided by 2 divided by alpha a. I'm just gonna, no, we're good to go. There you go, we got the right answer. So there you go. So there's probably my formula that I would use. Obviously we solved it right there, so this works too. But definitely this is cleaned up as much as I would want. So yep, pretty cool. Yeah, it's weird because you know what I mean. If you multiplied this by mg and then divided by mg, then you could factor out the mg's. But this is probably the cleanest that I know how to make it. You know, this is how I would use it. And yeah, that's pretty sweet. That's pretty sweet. And it's everything that I've ever wanted. I wanted to answer the problem. And we'll go back to what the hell it even looked like. So I wanted to figure out the stress in the cord, basic, and just there's only 2 input parameters, this L and B. So I think you see that, and that determines like where the string goes taut, and where the string goes taut determines the center of mass of that based on height, and we used the equations of circles to do that, and that was the best way, even though you could say that whatever this initial angle is, which is just inverse tangent of b divided by L, and then if you know that, times 2, so 2 tangent b divided by L is this full angle, and then the sine component of that, so if this is an angle, the sine of this angle multiplied by this is L divided by 2. So L divided by 2 sine 2 tangent b divided by L. Well, guess what? That's also height, and it's a function of L and B. So, I mean, I could go back through and throw this one in, but this one was just so much more satisfying because it was a function of b divided by that, and you got rid of the b parameter altogether. So that was pretty sweet. Alright, so I'm going to be done. That was the answering the problem in terms of total letters. But again, I guess I'm just going to finish with what I'm saying is that, you know, now this problem, given any L and B, and pulling it up till the string goes taut, will give you the max stress. So that's just kind of cool. I like it. Alright, thanks for joining me, and guess what? That's a video.